So what we're going to be going over today is really an introduction to scientific computing, I guess is how I would phrase it. We are not going to cover Python at all. We're going to assume that you have some background there. If you don't worry. I think that there's enough that it's not going to lose you in the process. But we'll cover the basics of using the IPython shell a little bit, and then we're going to cover Matplotlib. How many people have used Matplotlib? Okay, so I may be able to sit down and let you guys teach at that point. We're just going to go over really the basics. I think there's an advanced course by Ryan May in the afternoon. That's a good follow-on. This is really kind of a just the facts man version of that to get you enough knowledge so that we can then talk about NumPy a little more, and you'll be able to do, anytime you're doing exercises with NumPy, you're typically going to want to plot something at the end to see if I've gotten it right. And so you need to have some of the background on the Matplotlib side. And then we're going to move into NumPy. So the catch here is that the material in the slides is typically about a day and a half worth of class. And so what we're going to do is we'll probably skip a few things, but the main thing that we'll do is the exercises. You should have, I think everybody got an email with the zip file and all of that. Everybody have that installed? Does anybody not have that information? The zip files for the classes. So you should have the class notes and all the exercises. If you have those, then feel free to be working on some of those during class. We may spend 5, 10, 15 minutes on a few of those as we go through. But we're not, as we get to the end, we're going to leave the exercises to the reader, as they often do, right? Often do. All right. So given that, let me start up here. How do I go to view? There it is.
Anyone else who needs help with the zip file?
Everybody good? Okay, also everybody, I'm assuming, has an IPython shell installed, your favorite editor installed, and knows how to navigate a file system. Those are probably the pieces there. Uh-oh, I don't want this playing. Okay, so one of the options there is EPD. You may have grabbed that. If you're on Windows, I see a whole lot more apples staring me in the face than I see Windows machines. There's also a version there. And so you can install this, and then you can launch PyLab. You'll get a shell that looks like this. This is a DOS shell. I'm sure on Linux you're familiar with using the shell. But you ought to be able to fire up an IPython prompt. And when you start IPython, you want to start it with, on Windows, -pylab, or if you're doing it from the command line on Linux, I want you to do --pylab. And what this does is it starts IPython up in a special mode where it basically makes it like a numerical. If you're familiar with MATLAB, it provides you all of the tools that you're used to in MATLAB. It sets up so that Matplotlib is able to run at the same time that you're entering commands at the command line, and it also imports all of the NumPy libraries and SciPy libraries and Matplotlib libraries, so those are all available to you in the beginning. All right? And then let me just run over to one. I am going to be operating out of a beta of an environment that we have. That will be an IPython shell and an editor integrated together. It's not any, if you have an editor, you can do the same sort of things. Did anybody grab this? This was available for people to grab as well. The 8.04 beta on things. Okay, you do.
No.
You don't have it?
It flipped out.
It what?
It gave an error.
Oh, it did. Okay, well, we ought to check that. That's what betas are for. So we'll find out what that is. But we have an IPython prompt here, and then we're going to have an editor that we can use as well. I'd like you to start up your IPython prompt with me and make sure this set of activities work. You ought to be able to type 1 plus 1 and get 2. If you don't, we have an installation problem, right? So that should work. All right, you can say A is equal to 1, and you can say A plus 1. Do things like that. You could say A is array, and this is one of the things that you ought to be able to do. And you'll notice typically array is not a standard Python built-in data type. It is actually something that comes from NumPy. And so if you're just operating at a standard Python prompt, this line will fail. It will require you to do an import at the top of it. But if you start up IPython with --pylab, that should work. And then you ought to be able to say plot A. And we still have that where it shows up behind. We have a plot there that shows up. Does that work for everybody? Everybody able to do that? Does anybody have problems with that series of activities? Excellent. All right. So we're good from that perspective. All right. So let's get into doing things. This is what we've just seen. There are a number of commands in the IPython prompt that are nice to play with. You can type whos. That will tell you what are the variables that are available in the current namespace, or what are the variables basically that you created. All right? This is very MATLAB-ish. And if we have B is equal to 2 and C is equal to hello, then we type whos again. Interesting, we didn't get a C. So there's So C must have been there a priori. The way that IPython does this, it is a bit of a cute hack. What it does is it grabs all the variables that it has when it starts up, and then whenever you make a new one, it checks to see if that one was already used. And if it isn't, that's what it shows in the whos command here. And so C must have already been defined, and so it's being pulled out. Typically, though, this will give you the variables that you need to see. You can also use reset, and you'll notice I'm using, typically these are called IPython magic commands. I can type %whos. I can also just type whos. There's a difference between IPython commands and standard Python functions. And so if you want to run an IPython command, you have to type the % in front. So that gives us the whos. The exception to that is IPython will first, if you don't put the % in front of it, it will check to see if you have a variable named that. If it is, that's what it gives you back. If it doesn't, it'll check and see if there's a magic command that's available, and it runs that. So there's the %whos, and then you can do %reset, and that should, you'll see it gives you a command down here that says, do you want to delete all your variables? And if you say yes to that, now when you say %whos, there's nothing there. So this will reset your namespace. This isn't that powerful. I mean, all it's doing is setting back your variables. It's not like it's restarting IPython and clearing out all of the imports that you've made, all of the variables that you've made. Are you good? Okay. So are all of the imports, it's not like a reset of the entire system. All it does is it clears out any of the variables that you created at the command line. So it's not a complete reset of the system. Just be aware of that. If you do a reset and you still have something wonky going on, you may need to restart the entire Python session that you're in. And we can do that here with this tool. There is a way to just restart the kernel, and then you go back to a clean kernel. On that. You did not kill me. No. That's interesting. Okay, so it did do it. It just didn't reset the number. So That will restart your kernel. If you're at the command line, you're just going to want to kill your Python prompt and then restart your Python prompt on things. All right? Let's see. CDing around, this is a nice feature. If I do an ls, how many people are familiar with Unix commands? God bless you. So that's not always the case. So if you're familiar with Unix commands, now you have, in the IPython prompt, you have this combination of capabilities where many of the standard commands for navigating your file system are available to you. So you can do ls, you can do cd to class temp, and that puts me in this directory here where Zach's picture was. We have this set of exercises. This is the set of exercises, by the way, that you guys have on your file system that I gave you. And the other thing here is if you just type a part of it and then hit tab, it's going to do the tab completion for you. So you can cd down into that directory. And there's a really nice feature here. I'm going to go into NumPy. And here are a set of examples. There's a really nice feature in IPython called bookmarks. And I can say, I want to bookmark this directory as extra. And now I can go all the way back up to my top of my directory tree, and if I say cd to extra, then it takes me right back to that directory. This is one of my favorite features when I'm doing kind of data analysis and that sort of thing in IPython. You can go, you'll have some directory tree with files all over the place, one experiment over here, another experiment over here. It's easy to just change directories down into one and then bookmark that. Go back up into the next one, bookmark that, and now you can go back and forth between these really easily. I'll typically bookmark my temp directory and a whole lot of other places. And if you want to see what bookmarks are available, you can use this bookmark-L that will list them out. And you also have just general help that's available. If you want to find out all the commands that you can use with bookmark, then the IPython question mark is always your friend. That will give you the help message and be able to print out all the bookmarks that are available for you. Okay? All right. So you ought to be able to list out a directory here. We don't have the speed of light in this demo. Let me just come over here. Let's go to calc derivative. And here we can say, you'll be able to, I think you can use the magic edit command as well. On Linux, that will bring up a Vim editor if you want one, or whatever the default editor is in your system. But that'll pop up the file here. And we have this file that's available here. You can see what it does. It doesn't do a whole lot that's very fancy there. But if I come along and I say %run calc derivative, that will now run that file, and we're going to have that. Did we not have an image show up? Oh, it should have. I thought we had a. There's this picture. So if you just do %run at the IPython prompt, this will run that program that you just saw up here. It will run this program that's going to go import some files, do some calculations, and then does some plotting at the end. Now, one of the cool things about this is at the IPython prompt down here, you'll notice I created some variables up here, like x and y and dy and dx. Those variables are immediately available at the command line down here. Okay? So after you've run a script using the run command, everything that was a variable in that script is also available at the command line. And this is actually how I write my programs. I'll write a snippet of code, I run that code, I look at the IPython prompt and debug and look at the results. Why isn't this working? I go make a modification, I run it again, and keep going. Yes, sir?
I noticed that while I'm just running in a terminal, not in a IDE. And
Yes.
so when I say run calc derivative, it does give me my little screen, but it does not give me my prompt back. Is there a way to put that in the background?
So did you start with IPython -- pylab?
It's a Mac, I just did a single file app.
I think you have to do -- on the, try that and see if that's is that correct? Am I right on the OS 10 side?
Well, I got a crash when I did that too.
You got a crash. Boy, we're starting off really well, aren't we here? You
I got
guys-
the dash pile, it just sort of told me not to do it, and it's gonna work fine. So I'm getting a different version of it.
What? Wait a second. So, all right, so if we do IPython -- pylab, we have this, you guys, so we're running now. I can do something like A is equal to 1, 2, 3, and then I ought to be able to do plot A, and you ought to get a plot up. And you also ought to get your command line back. So I started with what? I started with -- pylab, I believe.
So just feedback, I just did it after doing dash pilot, and it's still the same thing. It does not give me a prompt back.
Interesting.
It's not giving us the prompt.
Nobody's getting the prompt back when you run it with -- pylab?
Once you get it back.
You do.
I do in Linux.
So how many people, so you're running off of, let's make sure that we're all right, let's try this. So we do IPython -- pylab, we start that up. So you guys see the same basic thing, this is the approach that you're taking. And you'll notice, I mean, what's happening is it's actually spawning an external thread. That's why we lost the prompt here. I have to, because it needs to use that for the plotting side of things. So I get that back, I say A is equal to 1, 2, 3, and then plot A, we're up and running. How many people does that not work for? 1, 2, 3. And y'all had problems back here as well?
Just with the script.
Oh,
With the script, not with just.
Oh, just with the script. Okay. All right, so if you do a run calc derivative solution, you don't get the prompt back. Okay. So everybody's able to do it if you just throw up a plot, but you're not able to do it if you run the script. What's that? It works with the script. Now, yeah, so this is the Heisenbugs, right? On things. It's completely different for everybody. Well, maybe at a break we can look at that and check that out for you guys.
I have a different question.
Sure.
You say when you run the code and then at the prompt you get all the value of those
Yes.
values. How about if you code another piece of code and then that code returns to this code and with all the variables available or just the main code?
It's just what was in the global namespace in this, so whatever variables are named at the top level in this script. Or in the under main. I mean, like, so there's so basically if it's in another function,
That's the
yes, I mean, they're put on the stack and then popped off the stack and they're gone.
good. Yeah.
All right, other questions? Yes, sir.
So should I expect run to behave more or less like a sourcing a script file in Unix, or is there any import magic Python style that happens when I run something with the magic?
Yeah, good question. So, no, there's nothing magic that happens on imports. In fact, this often creates headaches for people that are learning because you're used to having this, comfortable armchair of an environment called IPython, and array and plot and all of these methods are all available to you. As soon as you go and write a script, if you type just array in there, you're going to get a name error. You have to say at the top from NumPy import array. So in fact, it's explicitly not doing any import magic there. The way to think about it is it's like you clear out the Python, the global namespace, or IPython does. It runs your script, and any of those variables that are created there are then available at the IPython prompt, but nothing special happens at the beginning.
But the part where you said it clears out my global namespace, that's part of when I type run, I'm gonna lose.
You don't lose any, it's like it gives it its own little bubble of an environment. It runs it there, and then any variable there it brings back and just updates the local dictionary.
So it's when the script that's running is not going to have access to anything that was in my global namespace when I ran.
You're exactly right, unless you do, let's do this, print A. And let me save that very impressive example, test 2.5. So if I run this and I cd to, so I have, oh, I thought, where did I save that? Okay, so we have that file there. If I say run test2, it tells me that A is not defined. On the other hand, you can always do run question mark and get the help for it, and you'll notice it has a ton of options. And one of those that you can do is run -I, and if you do that, let's say A is equal to hello. If you say run, and what was that, test2? Of course, that doesn't work. I need the -I. And if you put the -I, what that says is run this inside of my current namespace. So in fact, a use case that I'll often do is at the beginning of a script, I might be creating a large data set. And I will do that. I'll run my script, and that takes like 20 seconds or whatever to do whatever it's doing. And then I have some plotting algorithms that I'm trying to get to work. I'll run that script the first time. And then whatever that data was is now available at my Python prompt. I'll go and comment out those lines while I'm working on my plot or whatever, and then I'll switch over to using run -I. So the first time I created this 20 seconds worth of data, and then the other times I don't have to go back and create it again. So it's just a handy approach to take on that. Yes, sir?
How do you set environmental variables if I want to set my editor?
Is there a way to do, I have never done this, but if we look at edit question mark. Yeah, there may be a way through %edit. There's also something called a Python RC file that's in, if you go to your home directory, there will be a .ipython directory, just like there's a bash RC and that sort of thing. And one of the things in there, you can scan down and it's fairly readable. And if you find, there will be an editor command and you can set that to Vim or Emacs or whatever. Cool? Yeah?
What's the name of the experimental code editor you're running again?
It's called EPD8. It's the next version of EPD.
Okay.
So there ought to be, can you find a link for that so that if somebody wants to run it, we'll make sure we have it. Okay. What else? You good? Okay. All right. Just a few other commands. I think we've seen most of these already. Print working directory will print out the current directory. We've run speed of light, or in our case, we ran calc derivative solution. Again, I really like the tab completion. You just type out as much as you need, hit tab, it will complete. You just have to be kind of to the point where it's unique. And if in this case we see at the if you hit tab, it's going to show you all the files that are available with that name, and until you get as specific as you specific enough to be where it won't get there's no ambiguity, it won't actually complete it perfectly. All right. So we'll be using that, or you will be in the process. We've already seen the question mark command. This is a nice feature in IPython to allow you to get help on a function. So if you're not quite sure that what a function means, then you can do len question mark and you're going to get help. Now there's squeeze question mark. I don't know why that's not there. Squeeze question mark, and it will start printing out, you know, the help for that. And this is just the doc string of the file. And if you put 2 question marks, that means I really, really need help, right? So if you do that, it will actually give you the source code. Okay, this is really a nice feature on things to grab the source code on something you're not quite sure how it's working. You have some routine, it's not working out exactly how you think it should. It's a cool feature. Just go grab that function, do the question mark, you can see exactly what the code is that's executing. This only works on Python functions. You'll notice if I try to do this on len, it doesn't do any more than just print out the doc string. And what it should have said, does it say? It doesn't say there. Typically it will say, I couldn't find the source file. The reason that it can't on len is a C function defined in the bowels of the Python source code. And it can't go and find that C code for you. The only thing it can print out is the Python code. So it will only work for standard Python functions. All right? We've seen a few of these. Tracebacks. So on occasion you will make a mistake as you're doing things. What I would really recommend you to do, a lot of times in classes people are like, hey, it doesn't work. And you're like, well, did you read the traceback? And the problem with that statement is the tracebacks are often messages only a mother could love, right? I mean, they're not really that helpful. On the other hand, there is some information in there that could be useful. So here's an example. If you said 1 plus hello, if we look at this, we get what's called a type error. And there are 2 things to pay attention to. The first is what kind of error occurred. And the second thing here is what is the reported message. And so this says there's a type error, and then it gets more specific to say unsupported operand type for plus, int and stir. Now, if that were in English, it would say you can't add an integer in a string, right? So you can sort of decipher that from this message, all right? But you can run very similar code. In this case, we're saying undefined var plus 1. So this might be some variable that actually I haven't created before. And if I add these, I get an exception too. And to the untrained eye that's just looking at running their code and seeing another error, they'll say it still doesn't work. Well, look down here and you see a totally different kind of error than you saw up here, right? This says there's a name error. Undefined var isn't available. It's not defined. So look at those, try to parse those exceptions. Learning how to read exceptions and understand where errors are occurring is the key to not getting very frustrated. Like it's a critical part of using Python. It's also nice because when something fails here, you get a traceback. In C, you get a segfault, right? So this is a little bit easier to kind of deal with. At least you have something. All right. Go through quickly. All right, so we are. So NumPy. NumPy is this foundational library that we're going to use for everything that we do. And if you think about it, I think about Python at the base. Right above that, I think about NumPy. NumPy is actually not part of the standard Python library. It's this separate package. But I often think about the Python language plus NumPy as being the equivalent of a MATLAB runtime. It really provides that set of capabilities. Python's the language. It has a whole lot of standard data structures. NumPy gives you 2 data structures, and really we only care about one. It's called an array. and it'll have this name called indie array underneath the covers. But that array data structure is what allows us to look at our numerical data very efficiently. Now, it's very slick. We'll spend a lot of time on it. Behind the scenes, there's this another data structure called a ufunc, or a universal function, that's critical to the speed of NumPy. And universal functions are any kind of operator that you would have that would operate on an array. So if you're looking at sine or cosine, all of these kinds of functions are actually universal functions. More importantly, all the binary functions like add, subtract, multiply, divide, all of those are ufuncs. So whenever you do a plus b later on, underneath the covers, realize that there's a ufunc there doing that. The likelihood of you writing your own ufuncs or using this infrastructure, if you're a casual user, it's just going to work for you behind the scenes. On the other hand, it's a really nice and powerful feature. You can actually write your own ufuncs and define new operators if you want to that will behave at the speed of C very efficiently. And yes?
I had a question for you related to ufuncs going back to your magic question mark.
Yes.
I always found that the NumPy ufuncs often had like scalar counterparts just in the math libraries in Python. Like I could take the sign of a number.
Absolutely.
But help was very unhelpful in a standard Python shell when I would try to ask for help about ufunc, because it would basically tell me stuff that was appropriate to every ufunc, but not actually about the trigonometric function I was asking. How did the question mark get so smart? That if I use IPython, it actually tells me what the functions do.
So the secret behind a lot of these things are their hacks, right, on what's going on. The question mark is just a convenience to pop up the doc string for whatever's there. And so whoever wrote the math library in the standard Python, when they had sine and cosine, they probably generated those automatically by going and wrapping math.h and exposing each one of those, and they may not have taken the time to write a nice doc string for each of them. When the doc strings got created for the sine and cosine and the ufunc versions of those, and they are completely separate versions of those functions. So they're really, I mean, they're a different memory address, and you know, they're wrapped up, they have different code associated with them, and they can also have a different doc string. So that's the most likely scenario there. So the second thing, so NumPy, we're going to spend all of our time down here. Please know that there are many other libraries. SciPy is actually a nice collection that you're probably aware of. That's going to be, what I think about is, this is the toolboxes, if you're thinking in MATLAB world. This is linear algebra optimization, tools for doing interpolation or signal processing. All of these different capabilities are here. And then, in fact, outside of this ecosystem, there are a zillion more. There's going to be, I think, talks on scikit's image, maybe on scikit's learn. There's tools like pandas. I mean, there's just an incredible ecosystem around all of this. We'll focus down here on NumPy today and on the plotting. These are just some stats on the tool set. They may even be out of date by now. I don't know how many downloads we have. Kind of the measure of success for NumPy to me was when I first opened up one of these guys, OS X laptop, and I could just go to the command line without starting up anything else. Start up Python and then say import NumPy, and it was there. So NumPy is to the point where it ships on some of these OSs. Now, if you know exactly what function, like you know, hey, sine's got to be a function in here, I can do sine question mark and get help on it. That works really, really nicely, right? That question mark thing can give you a lot of help. The problem is, what if you know, let's see, I know I want to do a singular value decomposition, but I have no idea what the name of the function is. Kind of that reverse lookup, the Google problem. right? There isn't anything currently in IPython that does this reverse lookup that nicely. So I will point out there is some good documentation on the SciPy website, and there's a page I particularly like, which is this NumPy examples list with docs. And if you scan down this, there's like 400 functions, and then there's an example for every one of these functions. And the thing that I like about it is it's all on a single page, so it takes a bit of time to load. But if you are looking for singular value decomposition, I hope you can just use singular, and somewhere down here we're going to get to a singular value decomposition, hopefully. Well, there's too many of them. There you go, singular values. Oh. No. Well, this is going to use up the whole, there it was, singular value decomposition, SVD. So this is a poor man's way of trying to find what are all the functions. If you're looking for least squares, there's probably going to be 2 or 3 things in here. It's not the world's greatest search mechanism, but it works pretty well. All right. So you might want to have this file open as we're doing things. Probably won't run into too many today, but I use that quite a bit. All right. So we're again using the --pylab to start things up at the command line. An alternative, if you're not using if you're not using that command, if you just start up IPython, you can also type from NumPy import star at the top. That grabs all of the variables that are in NumPy, puts those at the command line. That's a convenient way to start up if you don't have IPython around, as you can use it in a standard Python prompt. It's very bad manners to do this at the top of your scripts. All right, let me repeat that. It's very bad manners to do this at the top of your scripts. So you'll see people sometimes put this. It's very convenient because you have all those variables available now. But when somebody else is coming along and trying to debug your code, it's very hard for them to figure out where maybe some of these functions came from. Okay?
That's somebody maybe you 5 years later.
That somebody maybe you, yes, exactly. What is it Paul Graham's thing? It says have empathy for your end user or your reader, because in 6 months it's going to be you. You need to be careful about the shortcuts that you take. So I like being much more explicit. If you're going to use in a script, if you say from NumPy import and then the names of the functions that you're going to use. Okay? So let's just look at how arrays work. So let's imagine we created 2 arrays here, and let me just go back to the prompt here, clear this out, and say A is equal to an array, and I'm going to have 1, 2, 3, and we'll come back to all the different ways. Goodness gracious. Can I do %pylab to have all of this? That will reset your namespace as well to all, making sure all the variables are there. So I have 2 arrays here, A and B. If I say A plus 1, the way this works is A here has the variables 1, 2, and 3 in it. If I add 1 to this, remember, if we're in pure Python and this is a list, it's not going to work. You can't add a list, an integer to a list. But in NumPy, when you do this, this is the same as adding 1 to every element in this array. 1 plus 1 is 2, 2 plus 1 is 3, and 3 plus 1 is 4. It's basically an implicit loop. You're looping over that array and adding that scalar, the value 1, to each element in that array. All right? If I do A plus B, again, if we were in Python and these were lists, this would be a concatenation operation. But in NumPy, this does an element by element addition. 1 plus 2 is our 3, 2 plus 3 is 5, and 3 plus 4 is 7. So this is the equivalent, if you come from MATLAB land, of a dot plus or a dot times. dot plus operation. It's going to be element by element. This is very different than, Python is going to do this on everything that you do. Every operation you do is always going to be element by element, unless you explicitly try to cast something to a matrix. So you're never going to end up with an A times B and end up with a matrix multiply or something like that. If you have 2D arrays, they're always going to be element by element operations on them. Okay? You can also do things like A star star B. Anybody, what does star star mean? To the power of, exactly. That means you're a Fortran programmer if you know this, right? Or you've used Python. Those are the places that you see this. So A star star B is going to take every element in A and raise it to the power of every element of B. And so this is, again, element by element. It's not like a Cartesian operation where it does an outer operation on these or anything like that. We're going to raise 1 to the second power, which is 1, 2 to the third power, which is 8, 3 to the fourth power, 81, and 4 to the fifth power, which is 1024.
Question.
Yes?
I noticed there's a slightly different syntax that you're using to define the arrays A and B. You use the inner brackets, and in your other screen, in your the soft brackets in the previous screen, you're using the hard brackets in this particular example.
Yes.
Is there a reason for that?
So the deal is that array is actually a function. It's actually a casting operation. And so anytime you use this, let's say I have a list. If I say array A, that converts that to a list, or to an array, excuse me. If I have B is equal to, that's not a list, that's a tuple. It's a different sequential data type in Python, but it's still a sequence. It's an ordered sequence of items. And so I can say array B here, and I get exactly the same thing. So the reality is that array is a casting operation that can take any sequence and convert it into an array. Cool?
Thank you.
Uh-huh. All right. Other functions that are worth playing with here, we have A is equal to A range. You may be familiar with range. A range is the same as range, except that it creates an array instead of a list. And you'll notice two things that I've done here. If I do this, well, precursor to things we'll see later, that gives me a slightly different result than that. Who can tell me what's happening there? What's the difference between those two?
Base data type is an integer instead of a real.
Exactly. So whenever if I do type in Python of 11 dot, it tells me that's a floating point number. If I do type of 11, that's an integer, right? So whenever I use 11 dot, whenever we create an array, we end up with an array of floating point values. We'll come back to this later on. If you just do 11, then it's going to be an array of integer values here. Okay? All right, so if we do that now, so now we have A. So if I do A times, I don't know, 2 times pi over 10, then again, we're just doing a scalar operation on this. So I can say B is equal to those values, and then I could say C is equal to sine of B. And now what we've done is I've converted, I have values between 0 and 2 pi here, and then I've taken the sine of each of these values, and we ought to be able to do plot B versus C now, and I ought to have a pretty plot that comes up. Where's my pretty plot? Why am I not getting pretty plots?
It was on there. Came on.
There it is, okay. So there's the plot. Now, it's not a very high resolution plot, all right? We only had 10 values, but you can clearly see your sine wave there. And this is where the power lies, I think, is you have this elegant kind of way to express numeric things, and you have this nice plotting library to bring these guys up.
One of the, you can only plot one between.
It's going to plot, in this case, what it's doing is plotting B, which is really, I should have named them X and Y. It's plotting B versus C there. Cool? All right. So that gives you a quick rundown of what you can do with these guys. We'll be using Matplotlib a whole lot, and so we'll take a bit of an interlude here and go over the basics of using this. Okay? So Matplotlib is this really slick project, and it has a great website. I would encourage you to go poke around there if you haven't before. You can even do it now. One of the really nice places to go is this gallery on things, because it's going to give you a list. Let's see, is there a picture with the gallery? Well, let's go to, do I have it up? Yeah, so if you go to the Matplotlib library, the gallery is kind of, there's good documentation for Matplotlib, but there's also, I love this sort of learning by example. So if you see a plot, that's the plot, you look at that plot and you go, that's exactly what I want to do. You can click on this guy, it shows you what the plot is, and then it gives you the source code. And so you can take that source code and you can run it. And you should get the same picture of it. And now you tweak till your heart's content to use your data, right? So really nice kind of feature. And it's also a quick way to kind of run down and see what kind of pictures are available, what capabilities are there. And the answer is there's a lot, right? So the website's nice. There's also some good documentation there. We're just going to run through some functions fairly quickly here to give you a sense of how you would do different things. All right, so let's create a line plot. Here's another function that I didn't show with linspace. How many people are MATLAB people, by the way? Wow, okay. That's interesting. Not that many here. Linspace, a lot of these functions you'll see will be very similar to what they are in the MATLAB world. Linspace gives you an array from 0 up to 2 pi with 50 points in it. So it starts at 0, goes to 2 pi, including the endpoints. That's kind of different than a lot of the Python functions. And now we're just plotting the sine of that, and we get a single plot up here. The plot command, again, mimics MATLAB's syntax. So if you say plot x versus sine of x, then in this case, if you just say plot sine of x, you'll notice on the bottom this goes from 0 to 50. It's on the x-axis is just the index of your array, and on the y-axis is the value that was in the array. Okay? If you want to be explicit about your x-index, then you can specify x versus sine of x now is not going to be 0 to 50, it's going to be 0 to 2 pi that gets plotted here. But look at this, we put 2 lines in here. So x versus sine of x and x versus sine of 2 times x. So we double the frequency and you'll get the green line here. The deal there is the plot function is this uber function that tries to interpret what your intent is. And you can do a whole lot of things here. As long as you're putting pairs, x versus y, x versus y, x versus y, it will add all of those lines to the screen. Okay? The other thing you can do with this, let me go over here and I'll come back to that, is you can add a formatting string. So you can say, I want to plot x versus sine of x, and clearly this means I want you to make a red line with triangles on it, right? Obviously. It's not so obvious, but that's what it means, and if you're an object-oriented programmer, you kind of just shake your head on this stuff, right? But the reality is, this is super powerful. Like, there's so many times where I don't want to create a plot object and then go set the color and set the line type and all of these things. This is a really quick way to set up a whole lot of features, and it turns out to be a major part of what you need to do. So if you go and look, here you can say plot question mark. And this function can be intimidating because of all the different kind of options that are there, but the documentation is really nice. You can see all the different format strings. Remember, I did a dash here, and all of this information around this is markup. And it's not that heavy of a markup, but you have to realize that some of this stuff, like all of these characters here, are just used because this is what's used to create the documentation as well. And so you have to ignore some of that markup and realize that this is just the dash character in here. The description is the solid dash line, and on down you can see all of the different things, formatting the line type, formatting what the marker type is. If you just put an O in there, it's going to be a circular marker, and so on. And there's also colors. You know, you have blue and green and red, so there's only a few of them defined that are available, but there are other ways to specify colors as well. You can specify an alpha value. There's all sorts of capabilities in here about, you can specify labels, line widths, marker sizes, and you just have to go through and read as you want more complex capabilities. All right? So that's the plot command. When you create a plot, at the bottom you're going to have a few little doodads that you can press on, and they'll allow you to do various things. So let's just create our plot. So we have a plot here, and I can grab the pan tool and move this around. And move down here, and then might come in and zoom in on one area. And I decide, you know what, I want to be back where I was. You can use the back arrow. It's like a browser. It will allow you to go backwards and forwards to different zooms. And then if you hit the home, that will take you back to the original settings. You can save it out to a file. There are actually capabilities here to adjust the boundaries, on your plot. You can do all of these programmatically as well, but they're nice to be able to do them from the command line or from a UI as well. So that gives you the basics of just creating a simple plot. The save function, that'll save it out. There's also a command called savefig that will do this as well. We'll probably see that later on. All right, so scatter plots. You can also call, instead of the plot command, you can call scatter, and you'll get just the dots printed out here. And in fact, you can do this with the plot command as well, right? I could say plot x versus y, comma b0 as my string, and that would say make blue circles. And that would be exactly the same as this. So why do we have it? Well, there are actually more capabilities to scatter plots. And we can see that those over here. I created random arrays x, y, size, and color here. I scaled size up a little bit. Instead of being 0 to 1, it's 0 to 30. And then I call scatter with 4 parameters, the x versus the y versus the size versus the color. And what we end up with is a pseudo 4D plot, right? We're mapping four parameters into a 2D plot. We have the x and the y here, and then the size is varying of each one of these things, and then the color is varying as well. And you can set the color map if you want to a different color map. There are all sorts of options on these sorts of things. Just from you need to be careful when you're using size on your plots as something to denote a change. Because when you change size of a circle, you're changing actually the area, which is squared, and so you can have kind of skewed views of what your data is actually saying to you visually through that. But color always works fairly well. So just be aware of what you can tell people maybe incorrectly by changing the size on your plot values. multiple figures. You want to set this up. You just want to have two plots up at the same time. The way you can do that, you have your data here, and now I can call the figure command, creates a new figure, and now this is like a state machine. As soon as I've created that figure, if I do any plot, it's going to happen in that figure that's the current active figure. Okay? So we created our figure, we say plot x, which is the sine wave, and then we say figure again. That creates a new empty figure, and we plot that, and we're going to get the y value there. So again, we come in, and I can say figure, and you don't even have to save the figure out. You can say plot 1, 2, 3, and we should have, let me go and kill figures actually here so that we're, let me do, was the wrong one to pick up. I'm hitting the up arrow, by the way, is how this is, you know, I'm cycling through my old variables so I don't have to type them every time. So if I just type figure, I get a blank figure up. If I say plot, I fill that with a plot, create a new figure, then we get a new figure up, plot, I don't know, 4, and that ought to have a kink in it now. So now we have two figures in place, one behind the other. Sometimes you want to do that. Sometimes you want to put them on the same plot. And there are multiple ways of doing this. We've already seen overlaying them. If you just call plot and then plot again and then plot again, it's just going to accrete those plots onto the same one. They're just going to overlay each other one after the other. However, there's another way of doing this. We can say subplot, and I want to have 2 rows. I want to have 1 column, and I want to have the first one as the active plot. That's what this subplot command means. So subplot is making a grid. It's how many rows do I have, how many columns do I have. This can be 2 by 2 or 2 by 3 or whatever you want. And now we've activated the first one. Any plot command that I run is going to display in this upper plot. And as long as I'm on that plot, it's going to build up and add new plots to that guy. All right? So we've plotted this kind of triangle up here. Now I activate the second plot, and any plot command that I run now is going to plot into that lower plot.
How do you clear a plot?
CLF. And it has to be open close. It's a function call. That stands for clear figure. On things. Okay? So this is really handy if you're trying to build up maybe 2 plots on the top and 1 on the bottom, that sort of thing. Multiple plots, we've already seen this. They just get added to this plot. If you want to turn this off, then you can use this hold command. So by default, hold is on. The values that you put into the plot are held there until you put in, while you put in new ones. If you call hold as false, now you kind of change the state machine. It's in a state where it's not going to hold the old values. Every time you put a new plot in, it's going to overwrite the old one. All right? So you'll never, once hold is set false, every plot you make is going to replace the old one. It's not going to overlay it. So that's a nice feature if you're doing things, if you want that feature. Labels. Labels are really nice if you're trying to make something that you want to have a legend on. You can sit here and say, I want to plot sine of x. Because we have keyword arguments in Python, you have this nice ability to say, I want my label to be sine and label to be cosine, and then you can call legend, and up they pop. All right? You can also do this after the fact. You can call legend, and you have to remember what order you plotted things in and give it a list of the labels. This is not nearly as handy as this. It's just API compatible with MATLAB. So I would recommend you do this. All right? The other nice feature about this is imagine you have 10 data sets that you're plotting, but in the end you only want to label 2 of them, but you still need the other data up there. If you just put labels on those 2 plots, like when you call the plot line, if you only put a label on the 2 lines that you cared about having a label on, those are the only 2 that will come up. The others won't have a label put on it. That's handy. All right, titles. You want to put a title on your plot. Here we have plot x versus sine of x. Here we have x label. We have radians down here. We have a y label of amplitude. You can put keywords on here. Again, you want to figure out what these are. You go to y label question mark, and you get help on what are all the keyword arguments and how do I set them. And when you set the font size, you can't put like 10 point or 12 point or anything like this. It's going to be kind of a fuzzy value, like small, medium, large, because it's actually going to do this in comparison to other font values in the system. I sort of wish you could do the 10, 12, 14 point, but it doesn't work, right? You have to use these. So you have to go and look, and I think there's tiny, small, medium, large, extra large. I mean, you just have to go and see what they are. And then you can also put a title on the top of the plot. Enabling, if you call the grid command, you get a display of your grid down here. And we had the question, how do I clear a figure? If you create a plot and then you want to clear the figure out, you call CLF. All of those values are gone. If you have a window and instead of clearing, you want to actually get rid of the window, you can call close. That will close the active plot window. If you have 5 plot windows and you call close, it's going to close whichever one is the active plot or the one that you interacted with last. Okay? If you want to close all of them, and I do this sometimes, I'll have a script that I'll run and it will generate 30 plots because it'll go through and step through some values and I'll kind of just pan through those things. And it's kind of painful to have to go and click through all to close them all. So you can use the close and then give it this string all, and all of them will disappear. That kills everything. Image display. We've grabbed the Lena image out of SciPy here, and we're going to display it here, and the function for doing that is called IMShow. So we can put up this image, we can have a number of keyword variables. Extent is a nice one. By default, if the image is 256 by 256, then if you look on these bounds, it's going to be 0 to 255, 0 to 255, right? But if you know that this image has different endpoints, then you can specify these as xmin, xmax, ymin, ymax. And that's what these are going to get labeled as. All right? So now it's on the right scale. And then you can switch out the color maps, and there's a whole host of color maps available to you. And the place to find those is in the CM module. You can see all sorts of color maps here available to you to use. The bone, copper, jet, all of those different ones are available. It's pretty much, again, mimics a lot of the ones that are available in MATLAB. Then you can call color bar here, and that's going to display what the actual scale of your data is on the right-hand side. And you'll notice that, well, maybe this one's not, yeah, it's going to, it sets the dynamic range for you, right? In this case, we didn't go 0 to 255 or anything like that. It actually looks at what's the max and min value on your image, and then it scales the color bar to be, or the color range to be that range, so that you get as much dynamic range if you want. Sometimes that's not what you want to have happen, right? Sometimes you want to explicitly set those. And there's a keyword that you can set. I can't remember. Let's look right quick. IMShow. It's vmin and vmax. So you can set these to say, I want the lower end of my color map to explicitly be at -10 and the upper end to be at 30 or something. And that will limit the color bar. Or not just the color bar, but the mapping of your image to that range. All right. Let's see, we're coming down the home stretch here on, wonderful. Let's restart. At least it came right back to where it should be. All right, so scripts. Everything we're doing right now is on the command line. All of my examples are there. we can create a figure, have a plot of it, figure and plot, and you'll notice those plots are coming up immediately for me, right? It's not going to happen when you do it in a script and then say run. And this will be a source of consternation for you at least once in your life. You're like, where are my plots? They're not coming up. The thing you have to do is you have figure, plot, and then at the end you have to call show in any script you have. Okay? And the other thing that should be shown here isn't. If you write this as a script, you're going to have to say from PyLab import figure, plot, and show. Right? Because they're not available in the script automatically. You have to be explicit inside of your scripts to make sure that you've imported those values. All right? Without the show, the reason that MATLAB or Matplotlib does this is instead of always updating those plots in real time, which can be really slow, it waits and gives you the chance to say, okay, I'm ready to see those plots now. And that will make it where your scripts run much more quickly. There is a way to turn interactive to true. There's a function method called interactive. And if you call that, or a function called interactive, you can say interactive true, and now your plots will come up live. Did you have a question?
It was about the interactive mode, and you wanted to show kind of an iterative progress.
Yep.
Is it more efficient to use interactive, or is it better to call show explicitly?
It's what I've noticed is this is one of the areas where Matplotlib will sometimes get confused on things, or what the internals don't do what you might expect it to do at the top level. So whenever you want a plot to show up, it's nice to put show. It'll force it to bring that up. All right? Yes, sir.
Just on that, does that overwrite, every time you call show, it overwrites or creates a new problem?
You can only call show once.
Is that, you can't do it in the loop?
I don't think so. I think you can only call it once.
How do you do the, no, you can call it, if you want to do an update on a plot?
I don't think you can call it more than once. I could be wrong, but I read it back.
Yeah, this is one of the areas where it gets a little tricky on things. But you can have a plot that's updating live. And you might ask Ryan May what the latest way of doing that is. I think I've used show multiple times when I've done it in the past. Anybody else have knowledge on that specific issue? No? Okay. We'll check it. We'll do an example here in just a minute. All right. Histograms. The histogram is a really nice function in that it both does the histogramming of your data and it displays it. Here we're creating a random normal distribution of 1,000 values and calling hist on it. And that will give you your pretty histogram here. You can give it 30 as a second argument. And that's just saying, give me more bins. I like this function a lot because it's quick to get just a view up. The thing that I've noticed about hist is if you do it it'll work on 2D and 3D data as well. If you give it a big image, it kind of chugs for a long, long time. And so, an unnecessarily long time, and I'm not sure what's going on there. But there's the SciPy stats module, and that has tools for doing your own binning. And so, it's not quite as convenient. You're going to have to take 3 lines or so to do your own histogram. But those will work. It's very efficient. It works on a high number of data points. So if this turns out to be slow, go look at the SciPy stats module. There's also 3D visualization. I have not used this as much in the Matplotlib side, but it has some gorgeous plots that you can put out now. In this case, we create a figure. We're calling a method called GCA, which is get current axis, and we're telling it to make it a 3D projection. And now we have this axis. You can call different 3D methods on this axis object. In this case, we're saying plot this surface with different values, and we get this kind of bat display here for the data that we had. There are other kinds of plots that you can do. If you do plot surface, it gives you a plot like this. If you say plot, it just gives you a line plot in the 3D space. And I think the output is really nice from these things. The one drawback you're going to run into is if you have large amounts of data, this isn't going to be that efficient. And so if you need more performant approaches, there's another tool for 3D visualization called Mayavi. And it has a nice interface. Prabhu Ramachandran wrote this. And then Gael Veracol has done a huge amount of work to get the kind of command line version of these methods to work really nice. And so you can import from Mayavi, import MLab, mlab.surf, mlab.scalarbar, and this is using BTK to do all of this. I think out of the box, I like these plots better. They're prettier. But the power of this one is like an order of magnitude greater as far as the number of things it can do and also the speed at which it can do them. All right? All right, so more details over on the Matplotlib page. I think we will. Let's do an exercise lest you fall asleep on me. So team up with a neighbor. Look around and see who's the least objectionable person on either side of you. If you're on the end, I apologize. You only have one choice. All right? And you can work with that person. And so what I'd like you to do, so what I'd like you to do is, you should have that directory available. And I'd like you to go into exercises here, and then CD into NumPy. And then there ought to be a directory called plotting. And it has these these files in it. And so you can just open, if I say edit, in this case, plotting.py. Then I get my plotting file up here. And you'll notice that there is a big document string at the top. And this is basically your task. This is what you're supposed to be attempting to do here.
Which directory are you in?
I am in exercises NumPy plotting.
We have a student folder first.
Oh, you have, okay, yeah. So instead of class temp, you'll have student exercises NumPy. Is that it? Cool. Everybody able to get there?
Was the link ever found for EPD?
Did you? Do you have the? You have it.
If you go to the regular EPD webpage, there is a link there.
Okay. So it's right here.
Oh,
So you just go to nthought.com, go to the products page for distribution, and then on the right-hand side we have the EPDA page. Cool?
it looked really cool.
Yeah, it's getting there. So if you get this, the other thing you can do to change directories from this is if you want to go to that directory like plotting, you can just drag that down to the command line and it will CD to that directory for you. So either one of those will work. All right. So what we're going to do is try to create a plot. I want you to create a plot that looks like this. And there are a few commands that I left out. One of them will be called axis. I'm just looking at this to get, if you create a plot, let's see, if I say A is equal to, or X is equal to linspace 0 to 2 times pi, and we'll put 51 points in here, and Y is equal to sine of X, plot X versus Y. When we, oh, I had my new figure. So we have this plot. You'll notice I have a white gap on the end down here, right? And that is because Matplotlib guesses at what you want your endpoints to do, and it usually guesses at round numbers. It tries to kind of frame your data as a -1 to 1 and 0 to 7. But you may not want this. You may want it to trim on that end. So the way that you do that is there's this command called axis that you can look at. And it's going to, there are different versions: scale, tight, auto, image. Image is going to make it where you get a square image to try to get the pixels the same size in X and Y. The tight one, if I do axis tight, now if I go back and look at my plot, it's fit right as tight around the data or around the plot as possible. Okay?
Do you have explicit like in MATLAB where you say min max?
Absolutely. So there's all sorts of, if you look at it, in fact, that's what it spit back out to me. But you can either get the string or the values. And I think there's even keyword arguments, so you can specify just one of them. So the keyword arguments give you a lot of wins actually over a positional API. Okay? So what I'd like you to do is try to create that plot. And what we're going to do here is I'm going to leave this picture up. A lot of the commands are kind of given for you as far as at the beginning, reading the data in. And what time is it up there? It's like 9:20. Let's take about, say, 12 minutes or so. It's a little fast. Let's finish this at 9:35. And so we'll be working on this. And if you have questions, raise your hand and I'll come by and talk with you while we're working on imports that are given for you, and that'll be a helpful thing as you go through other examples as well. We've gone ahead and we've read in the data. A few of you had problems with this. In general, everybody, it seemed like, had a pretty good installation in place. There were a few people that didn't have Phil, the Python imaging library, and so they had to go grab that. But once that was done, easy install, worked like a snap, and that was very nice. You guys can't quite appreciate the difference in tutorials this year versus 6 years ago, where the first hour of the tutorial was always spent trying to get people's installations to work with all of the tools that you needed. So it's really nice to come in and it just works for most people. All right, so I've done a close all here to clear out everything that's not entirely necessary. But then make sure you start with a fresh plot. You could have also said figure. We do a subplot here, and we've set up that we want to have 2 by 2 activate the index 1 item. We want to have a plot here of the x versus the sine of x, and then x versus the cosine of x. And we're going to do the first with the blue line, and the second with red plus marks. And here's the little piece that we didn't have in the slides, this axis tight. You can be explicit if you want to and give it an x min, x max, y min, y max to be totally explicit, but this will try to pull it down and make it where it fits around the data exactly. And then here we have our second subplot, 2 by 2, activate the second one. And we're going to plot x versus s, and we're going to get some grid lines, or we're going to get radians, amplitude, and sine, and then we set up a grid line on this. And then the final one down here, we're going to set up a plot, activate the third plot, so that's the lower left-hand quadrant. It's 1, 2, 3, 4. We do the IM show, we set up the extents here to be -10 to 10, have a nice winter color map, and then tight layout, which is actually a new function. That one's new to me. We used to do an adjust. There's also a command called subplots adjust that will give you the right a better layout. Typically, before you call this, you're going to have overlap of your labels onto your other plot. All right, so if we do this, we'll save that. I'll run this. And down here, we just have the save fig, so this is writing this out to a file as well. And this is going to, you'll notice I save it out as a ping here. I think this will support JPEG. I think it will support SVG. Does it support EPS? Probably EPS. And if you just put that suffix on your file, it will pick the right one for you. So let's run that, switch over to that plot. And you'll notice we have this overlap here that we don't like. One way to fix it is just make your plot bigger. So that'll work. If you don't like that solution, you have this little guy here that you can grab, and this, you can adjust your W space, and that's the spacing in the width direction to get that right. And if you use the command, there's another function called subplots adjust that basically is the command line version of this little UI. You can specify each one of these things independently to get that set up. Or the tight adjust looks like it does it automatically, which is kind of nice. Yeah, that's pretty cool. All right, how'd everybody do? Did you get along with your neighbor? Well, we don't have any gin out there to get you over the hump of dealing with them, but maybe the coffee will work. So let's take, yes, do you have a question?
I added a color bar and that's really sort of does.
Even with tight adjust, it screwed it up? So file, yeah, you might file a bug with Matplotlib or something on that. So, all right, let's be back at 10 o'clock. That'll give you 10 minutes to enjoy some cake and fruit, and we'll see you back there. If you have any questions, come grab it. Yeah, I'm very excited about what I just learned. Arthur just came out and said, oh, by the way, you know about the look for command. How many people know about the look for command? Well, I don't feel quite as silly now. This is one of the great things about classes. You have people come up and show you how you should be doing things, which is perfect. So the look for command is something that's now in NumPy, and you can type look for singular value, and that then searches through all of the NumPy functions and gives you back all the ones where singular value was a hit. So this is slick.
And it only does NumPy functions?
Arthur?
I think so, yes.
It looks that way because I would have thought it would have hit a whole bunch of SciPy. And I bet that like most things this way, this is reasonably new because I haven't seen it. It probably is fast enough to work on NumPy, but probably if you added all of SciPy, it would need to have an index formed on it.
It has a module thing that says module equals.
So you could add SciPy in? So look for that, play with that. My bet is it's a little bit slow on that, but still, I mean, it's faster than you looking around for something you don't know about. So that's a great way to find stuff. And it might be using an index on the back end. I doubt it. You'd have to have a full text index to do that well. Okay, what else was there? Oh yes, so a woman named Alexandra Pavlik just came up a few minutes ago. Alexandra, where are you?
Yeah, that's me.
She's in the back here. And she is actually doing her PhD right now on open source software. And so
Scientific software.
open source scientific software? Or just scientific software? Maybe I'll stop botching it and you tell them what you're doing.
My PhD is about software development practice, about how scientists develop software. And because most scientists are user developers. So my study focuses mainly on documentation in scientific software development. So if you write documentation for SciPy, if you use documentation for SciPy, and you would like to share experiences with me, please find me during the break and talk to me, and I'd be very happy to collect some data from you for my PhD.
So many of you have done a PhD, you know how hard it is to get information, and this is a little bit more of a social experience than maybe you had in your PhD, but it'd be very nice if you would just touch base with her and give her some information about what you're doing. So please do that. All right. You didn't know that you were both an attendee and a lab experiment in the same conference here. So back to NumPy. We've gotten enough about the basics of plotting, and as usual, I mean, we're not going to get through the scads of stuff here, but we'll move as quickly as we can. I do like to do a couple of exercises here to make sure that people are able to do and follow what we're doing. But we'll go as quickly as we can. All right, NumPy, an introduction to arrays. So we've already had, if you're creating an array, the main function that you're going to use is this array function that's really a factory or a casting operation that will convert, in this case, a list or a sequence into an array. And if you look at the type of that, it will be an indie array. But there's also this other type. And this is really critical. If you're used to Python, you know when you create a list, the list can contain anything. The first element can be an integer, the second one a string, and the third one a float. When you create a NumPy array, one of the secrets to the speed of things is that arrays are homogeneous. They contain all of the same element. Okay? Now, that's a bit misleading because the reality is that element can be a Python object. And so if it's a Python object, you're back to it being able to be anything. All right? But it's not going to operate nearly as fast if it's a bunch of Python objects as it is if it knows that it's an int32. Because if it knows that everything in there is an int32, whenever you say add this int32 to this other int32 array, basically what happens is it strips out and finds the pointer to the underlying C data or data and hands that off to a C function that does this really tight fast loop at the bottom that adds two integers together. And it can do that at blazing fast speeds, just as fast as C can. It turns out that when you do, for multiple reasons, if you do multiple operations, if you do A plus B plus C plus D or whatever it might be, that's going to be slower than can be written in standard Python or in standard C. By somewhere, depending upon how complex a thing you're doing, typically your ratios are going to be 2 to 5 or 6. If you write it in pure C, it'll be 2 to 6 times faster. If you do simple operations like sine of A or A plus B, those are going to be the same speed as they can be because it's using the same kind of algorithm at the bottom. So be aware that you're going to have some trade-off, but if you compare this to writing Python lists, it's like way, way faster, order of magnitude or more faster. So that's the secret underneath the covers is this thing called D-type or data type is how I think about that. And it can be a whole bunch of things. In this case, it's int32. If we look at this, an int32 means that there's a 32 bits in their integer or 4 bytes. And so when you ask for the item size, that spits back how many bytes are in each element in the array is going to take up. There's also this shape that will tell you what is the actual shape of our array. Arrays are multi-dimensional. Now, we use them a lot of times as just a 1D array, but typically they're multi-dimensional. So when you ask for the shape, because it can be multi-dimensional, it gives you back a tuple. And a tuple can have multiple values in it. Even if it's 1D, it's going to give you a tuple back with one element in it. So this is an array that has 4, its shape is 4 in this case. You can also ask for the length of an array, len of an array. If it's a 1D array, that's going to be exactly the same as the first element in shape. That's going to give you how long it is, right? If we do this, if we have A is equal to array, or let's just do A range 20. If I do len of A, then it's 20. If I do A.shape, then it's 20, but it's now in a tuple. Now the place where len works great for a 1D array, if you're 2D, what is that going to return to you? Anybody know? Say it again. It actually, that would be a great guess, but it chooses a different solution than that. So there's an ambiguity, right, on what it could choose to do. And what it does is it returns to you the length of the first dimension. And it makes sense if you kind of go through Python, because Python's looking at this as an array. If you have a 2D array, it's like it's a sequence of rows. So how long is that sequence? Well, it's the number of rows that it has. That's what it's returning to you. Okay? And then size is exactly what you just mentioned. Size is going to be the product of the shape. Size is actually how many elements are in this entire array. Okay? And you'll notice there are methods, or there are attributes. A.shape returns this. There's also a method, shape A. And you'll notice this throughout the entire API. We'll have an attribute or a method that's available on the Python object, on the NumPy array, and there'll also be a functional version. And this is largely legacy. In the beginning, we didn't have a lot of these things as methods. You had to call the functional version of it. But over time, it's been convenient to add those to the array object. And so you'll have two different ways to do things.
So is the array NumPy is column major or row major?
Yes.
Which one, column or?
It's either.
Either.
So this is one of the, I mean, we may get to the way you can have it either way. By default, it's going to lay things out in C order or in row major order on things. But he's talking about the memory layout underneath the covers. You know, C and Fortran, in their infinite wisdom in the 1970s, one group wanted one way, the other group wanted the other, and so we ended up with the memory layout of how memory was laid out being different. I know that the cost of that decision is in the tens of billions of dollars around the world. I mean, think how many people in this room have had to deal with that in something. It's huge. It's funny how much. It's kind of like Franklin fusing a positive and negative on electrons, right? If you would have done the other way, the dropout rate of electrical engineers would have been a lot lower for the first year. But it is what it is, right? So those little decisions matter a whole lot. So we have row versus column, and it matters for speed about how you write loops and things under the covers. It turns out that NumPy's array data structure will handle either one of them. You can put the order, the way that the header of an array works is it will either work for row or column. And that is largely hidden from the end user. Okay? But when you allocate an array, it's going to be in C major or in C order or in row major order by default. In fact, I think if you go in and do array question mark, there's this order parameter that you can supply if you want to ask it to do it in the other order. So order can be C, F, or A. I don't know what A is.
Something that really messy in the order.
Yeah, you'd have to read. I'm not going to try to interpret that right now. All right? But, all right. The number of bytes that are used, this is the element size times the size of the array. And then the number of dimensions is ndim. So there are a number of attributes that are available to you. So let's look at this. Python is zero-based indexing. So those of you that come from the Fortran world, take notice. Or MATLAB world, take notice. It's more like C. So if I want to get the 0th element of A, then I could ask for that, and that's going to give me back the 0. We're kind of a couple of slides here. Here's our 0 that we grabbed. If I want to set that value, then I can index it and set a value in, and now I've overwritten that value. Okay? Now, what if I wanted to fill in all the values of an array? Turns out there's a method called fill that will just write that value across the entire array. So this is a way to initialize the array with a single value. An alternative is, this is using slice notation, and we'll come to this a little later. But this is saying I want to assign from the beginning to the end of the array the value 1. Okay, both of these work just fine. I probably write this a little more than I write this. There are some hiccups or gotchas that you need to be aware of. These used to happen a huge amount more than they do now. With the advent of NumPy, some of the default arrays that get created, like when you call zeros or ones or identity, those used to return to you integer arrays. And so you would run into this problem all the time. Now they return you floating point arrays, so you almost never run into this problem. But the thing that can happen is if you have an int32 array type, and I try to assign 10.6 in, 10.6 is not an integer, it's a floating point number. So what does it do? Well, there are a lot of options. One of the things is it could complain and raise a traceback. Another thing that it could do is just truncate the value and cast it basically to an integer. And that's a floor operation in the standard casting. And so that's what it's actually towards 0, I guess, is the way to think about that. It just truncates the value. And that's what NumPy does. There's probably an argument here that it would be nice to be able to set a flag of what it should do, where you could raise an error. But I don't run into this as a headache nearly as much as I used to. I don't in any actually now. But you do need to be aware of this. The place where I run into this in the past is you would create an array that was supposed to be a set of weights or something that you were multiplying times something else. You would come in and start setting the values, and then you would it would go through all of your calculations and you get your results out, and they'd be almost right at the end, right? Because everything was just rounded off slightly. And you're like, what's going on? And so it would take a long time to kind of trace back to where the error is. So be aware of that. All right, slicing. It turns out that slicing and understanding slicing is it's the way that Python or NumPy does all of its magic under the covers. It's how you do all of your math. It's how you do many things. So understanding this is fundamental to your success with the library. So so let's look at this for a second. This is just a repeat of kind of what we do for list, but I want to point out the way, at least, that I think about arrays. There's two ways of thinking about the indices on an array. The first is you can just take about this as the 0th, the first, the second element. Or if you come from a C background, you start thinking about these as pointers and offsets, right? And so you're really pointing, the 0th location is the memory location that you're pointing at right before the first element. And then the indices are just offsets to the next ones. That idea works fairly nicely with how slicing works, because if I say I want to slice off from index 1 to index 3, what that says is I want to go from index 1 up to index 3 and get everything that's between those. So that will return to me 11 and 12. The other way to think about this is it's inclusive on the lower end and exclusive on the upper end. So when you slice, you're going to get 1 up to, but not including element index 3. Okay? If you think about these as being in between, then you always have these bracket whatever you're going to get out. Does that make sense to everybody? Cool. So that grabs my 11 and 12. I can also grab index 1 up to index -2. Now this is quirky, but this is how Python works. Negative indices count from the end of the array, so -1, -2. So this allows you to write this to grab exactly the same data set. That's nice instead of having to write, how many times in other languages have you written len of whatever the thing is -1, right? That's basically, or -2, or minus whatever the thing is to count back from the end. So Python just gives you a shorthand for doing that. -2 counts from the end. You can specify that on the front end, so -1, 2, 3, 4, that's going to start here and go up to index 3, so that will grab the same values. Cool? Now, There are also times when you may want to slice off the first 3 elements. Well, you could say 0:3 and that would work. That's one way of doing this. Or if you say A, open brackets, :3, we've omitted the starting index in this case. When you omit that starting index, it just defaults to starting at the beginning of the list. So that's going to slice off the first 3 elements. -2 is going to start at index -1, -2, and go to the end. It turns out that there's not really an equivalent to this unless you know what the length of the array is. If you want to always go to the end of the array, then you have to omit the last index. All right, so you say -2:, that's going to slice off the last 2 elements. Did I see a question back over here? No? Okay. And then this one, I guess I'll go back a few slides. You remember here where we wrote this? This is saying go from the beginning to the end because we omitted the first index and the last index. So when you do that, you're not specifying either one, so it just defaults to the entire array. And we're assigning the 1 into that. Here we're saying start at the beginning, go to the end, and then you can specify a step value for the last one. So this is saying give me every even value, basically. Okay? Does that make sense? Or not even, it's not even index, that's more accurate. What if you want every odd one? How would you get that? Start at 1. You could do every odd by saying if your array was A, 1:, go to the end. So we omit the end, and then we step by 2. And that will give me all the odd values. All right? That's a clever way of doing that on things. All right, let's talk about now, as I said, this is how you do all of your math and that sort of thing. So there's an exercise called calc derivative. Hopefully you know you're in introduction now. Let's just look at an example and let's talk through it. So imagine I have, how many people are comfortable with calculus? All right, good. We're pretty good here. This is not very fancy calculus, so imagine you have a data set that somebody's given you, and let's start at 0.5, and then 1.5, and then 1, and then 0.5 again. And then we have, oh, let's not do that. I'm doing the wrong one. 1.5, 2, and then 3. And then let's have y values. I'll just start at 0.5 here, and then we'll go to 1, and then we'll go to 1.5, and 3. So what do we have? We have 0.5, 1.5, 2, and 3, and then I'm going to start 0.5, 1, 2, 3. All right, so this is 0.5 and 0.5. That's my first data point that I'm going to plot there, okay? And then we have the next one is at 1.5 and 1. So we have a point right here. And then we had 2 and 1.5. And then we had 3 and 3. And so if we look at this, we have something that looks like that. Now, the job that we want to do here is calculate what is the slope of that line at every location. Simple, just derivative of the line. All right, so if we look at this, we can think about these. If we go back to Python, we're going to have 0, 1, 2, 3, the indices, right? Those arrays. And so let's talk about the slope of this line right here. How do I calculate the slope of this line? Somebody help me out. What is it? Just we need a ratio of 2 things. What are those? Perfect. So I have this delta y and a delta x. right? Here, that we're trying to come up with. Okay, well, I'm going to label this as, in this case, we have, let's just think about the dy's for a second. And I'm going to call this dy0. And then we're going to have a dy1, which is this one. And then we're going to have a dy2, right? So we're going to be a little pedantic about how we write this out. I want to do each one of these. So dy0 is going to be equal to, somebody help me out, how would I write that? It's not tricky.
Y0.
Say it again?
Y1 minus Y0.
Great. If I do this one, y,
2 minus 1.
and then the final one is y3 minus y2. Cool? Now, if we were going to do this in C, C sharp, Java, any of these things, how would you do this calculation if you had to do these? What would you write in? You'd write a for loop, exactly. It fits that model perfectly. If you write a for loop in Python, it'll work, but your speed is going to be lackluster at best. All right? It's not going to be what you want. So, NumPy to the rescue a little bit here. And the way we do this is we need to do this with just a basic math. If we do a plus b or a minus b, those operations, remember, happen really fast down at C. So how do we get there? Well, the way we can do this is if you look, these values right here are all in a sequence. And so it turns out that that is this set of values right here, right? And if I go and look at this set, those values are located right here. So they're all contiguous on something. So if I want to write this, how would I grab the red set of values here? If I wanted to write dy is equal to y, how would I index this to grab this set of values?
1 colon.
1 colon. And the other set of values?
Colon minus 1.
Colon minus 1. There's some pros in the room. And that statement right there is exactly the same as writing a for loop. You have an implicit for loop, and you basically look at what the template that you're looking for across your arrays is. In this case, you can, if you unroll kind of the thing, you can look at which slices do I need, and then you're kind of just taking this set or you're taking this set and you're almost putting them below and just doing a subtraction. That's one way of thinking about that, okay? If you get this, then you get how NumPy does things. I mean, this is what you have to get in your head. Now, this is one out of probably 4 things that are critical. So if we're looking to do dx is going to look stunningly similar, right? And now to get your derivative, if I said dy dx is going to be equal to dy divided by dx. And this is your calculation of the derivative. All right? So there's an example, and we've just worked it for you. I want to spend 5-10 minutes. Never works to do it in 5 minutes. But again, team up with your neighbor. There's an example called calc derivative. And work that guy really quickly. And if it takes you about 30 seconds to work, then there's a second example where you do a Riemann sum. And it's very similar, or some kind of sum, I think, a trapezoidal rule or something like that. The only thing that you don't know about that you need to is a function called cum sum. It's imported at the top. do a question mark on it. If you finish in 30 seconds, then you're advanced enough to go and read the documentation how cum sum works and figure out how to use that for your integration problem. All right? We'll spend 5 or 10 minutes there. Yes, sir.
Does this take to an additional copy of each?
That's a great question, and the answer is no. So whenever you do a slice, if you do a slice on a Python list, you always get returned a new list, a copy of the list. If you do a slice on a NumPy array, it always returns to you a reference. Whenever you
subtract the 2 slices.
So that's a new value. You're creating a new, so it definitely has to create a new array. Like
So
dx is a new array, dy is a new array. There's no way around that.
dx dy is then going to be a third.
That's exactly right. So you have all of these temporaries that are getting created under the covers. And that is why I talked about a 2 to 6 factor of 2 to 6 compared to, if you were going to write this loop in C, you wouldn't write 3 loops. You would write a single loop and do all of those things. You wouldn't have any temporaries. You would just get the value. And that's actually where the cost goes. There's actually cost there, and then there's cost in one other area that the compiler doesn't know as much about things, so it's a little slower to play that.
And one other question, is there a way to represent a sparse matrix?
There is, that's in SciPy, and there's a sparse library. And the sparse library, I think 90% of its functionality is actually converting between the jillion different sparse matrix representations that there are on the planet. So it has functions for doing that. And then I think their super LU is also included in there to do LU decompositions. The other library to know about if you're doing singular value decompositions, there's a library called DVC that comes out of MIT Media Lab, and they use it for a lot of things like the Netflix challenge and things like that, like AI type problems. And that one is nice for doing singular value decomposition. And that can like give you one singular value at a time or something like that instead of having to give you everything back at once.
What's the name again?
I think it's DVC, is that correct? Anybody use that library? No, the sparse matrix library, it's DIVISI. It's something like that. Other questions? Yes. Was everybody able to get that? Do we need to go over that one? The ideas there? How many people did the integration? All right, we got a few. Cool. How many people is this idea new to them? How many people have never written anything like this? Okay, so maybe a third or less, a quarter. So this is like one of the fundamental concepts for getting this idea in. And it turns out that we use it in 2D quite a bit as well. And I'm going to skip going through that one just so we can also talk about the 2D case in a little bit of detail. So how do you create a multidimensional array in Python? Well, you basically handed a sequence of sequences. If you handed a sequence that's just scalars, those are going to be treated as a 1D array. But if you hand in a sequence of sequences, in this case, this is the first row and this is the second row, then you get an array that's 2-dimensional. And now if I ask for the shape, it's 2 by 4. How big is it? Well, 2 times 4 is 8. There are 8 total elements in this guy. It has 2 dimensions. And now when you index with 2 elements. This is one of the elegant things about this language. Guido was able to add this for us after the fact, actually, or the way that it was written, it allowed us to have this hack. If you're advanced, then really what's happening is this is the index operator. There's a getItem method that is on every object that you create that you can override. And what NumPy does is at the get item, if the function that implements this, if it sees a tuple come in, which 1, 3 is a tuple, that it goes, this is a multidimensional indexing. And so that's a bit of a hack, but that's how it fell out of the language, and the way that language was implemented allowed us to do this. So it's very nice, the end result. And what we're doing here is, on 2D arrays, it's nice to think about this as the row and this is the column. So if we access index 1, 3, that's going to index row 0, 1, 0, 1, 2, 3, and we're going to replace the 13 with a -1. So we can write into there. It turns out that you can also index arrays with just a single element. I don't know, what is, if you do this in MATLAB, MATLAB treats the array as a flat array, and it just gives you the element out. I don't know what IDL does. Does anybody else? Does it allow you to do this? You index a multidimensional array with one element? Well, I don't know about that one. What Python does is different than what MATLAB does. If you index with a single element, it treats that as you just are asking for the index 1 row. So that's going to grab this row out of the array. A side effect of this is if you loop over an array that's multiple rows, if you said something like for so if I have something like I have array 2D, that's a two-dimensional array. If I say for row in array 2D, this is going to loop through and give me each row one after another. That is sometimes a handy operation to do. It turns out that you can usually do this just with kind of these slicing tricks and things like that. But it does turn out sometimes. One of the places where I have run into this in the past is you have a target in the middle, you have some kind of sonar source or whatever that's pinging the data, and you get a time series from this angle, and then another one, and then another one. And so you end up with a bunch of time series that are just from different aspects. Well, if you look at that problem, every row could be one of those time series signals. And sometimes when you look at this data set, you really think about all of those rows together, or all of those signals together as an ensemble. Maybe you need to get what is the, you want to get some kind of standard deviation to find out what the background noise for the entire data set is. You want to do that on the entire array. It's handy to do that there. Then sometimes you want to do operations on individual rows because you want to do it on a single signal. You might use this method for doing that. There are other ways to do it, but this is one of the places. So be aware of that. That also, you were asking column versus row major. It also turns out that by default, if you arrange your data in rows, which is sort of different than we do in spreadsheets, by default, you're in a faster mode of operation in Python. It's a little more natural in how the language treats it. And also the memory layout has those things contiguous in memory, so it's going to be a faster operation. Okay? Reading data in. One of the things, as soon as people see arrays, they're like, oh, get rid of the list. I'm just going to use arrays because all my data is numeric. And the one thing that arrays don't do very well, or I often say that NumPy should be called MemPy, because really you're looking at your data as, it's really a representation of a blob of memory on disk. You can't resize or NumPy arrays very well. It really is, this is what my footprint of my array is, and this is the description of how it's laid out in memory. So when you're reading data from a file, a lot of times people want to go, how do I read it straight into an array? And the answer is you typically don't. You read it first into a list, and then at the end you convert it to an array. So this is just an example of code where we're reading through, we open a file, we read each line, we convert each element to a float, and then we append each row as a list. We append rows to rows, so we get a list of lists in the end, and then at the very end we convert it to an array. If you have to parse one of your data formats, this is a typical way of doing it. okay, if you have ASCII data that comes in. I'll also mention that there are these great commands. There's one called load text and one called gen from text. And they have similar capabilities. There's a trade-off between them. Load text works oftentimes. And imagine you have this data set. I apologize for this wrap. This power should really be over here. But in this case, you can have kind of multiple lines in the file, and then we have different rows here, and then some comment at the end, and then maybe some comments on a row. Well, how can you read that? You could write a parser that does this. The faster way is just to use the load text function. You can tell it the file. You tell it to skip the first row, so it's going to skip this row. And then you tell it the data type. All of the values that you're going to read in are ints. And then the delimiter between things is a comma. And I only want you to grab column 0, 1, 2, and 4. So it's actually going to skip this column right here. It'll just get 0, 1, 2, and 4. And then ignore any line that starts with %. So in fact, the skip rows wasn't important unless I guess that's it would be needed to skip that line. So this is one of the functions to go and learn about. The other one is called gen from text. Both of these are handy for reading in data. All right? Those are for reading ASCII data. For reading binary data, we actually use structured arrays, typically, or memory maps on top, memory maps of NumPy arrays on top of your data. And we'll be lucky if we get there today. All right? But it is very handy to use those as well. There are slides on it at the end. There are a lot of other data file formats to know about. NumPy does pretty well with text files. CSV, there's a CSV reader and writer for CSV is comma separated value. It's what comes out of Excel. There's a reader and writer in Python that read those files. And it would look somewhat similar to this. And how you would use it. SciPy.io saves and reads MATLAB file formats from 4.0 back or whatever. There's a point at which MATLAB switched over from their own format to a HDF5 format. If you have a newer MATLAB, when you save things out into HDF5, then you use H5Py or PyTables to read those files. NetCDF file readers are available. And then a number of others for the different file formats. I think I saw there are several astronomers in the room, and so PyFits, I'm sure that you've had fits with. It works pretty well, actually. So that's one of the tools. Okay, and then we saw PIL. PIL has been around forever for reading and writing all of the different image formats, and it's really handy for being able to grab those things.
Do you have any examples
of what?
Do you have any examples of read the CSV file?
CSV file there, it actually, we took that off of the slides and put on a different one, actually. I was just looking at that there. But I think if you just go and look at the CSV reader, just Google for it. So I don't have an example on these slides. It looks very similar to this, except you have to create a CSV reader. And loop over the CSV reader. But other than that, it's very, very similar to this. This is just reading from a straight text file. The other thing is a lot of CSV files, if it's just data, if it's just numeric data, you can basically use load text.
Just load the CSV file.
Well, you look at this, and this is comma separated. It works just fine for loading that in. The place where it won't is CSV has very specific format for how strings are put in. So if you have string data in there, then to handle that, then you have to have the CSV reader. The other deal is because of that, the CSV reader will be slower than just a text reader. Not much, but if you're dealing with huge files, you may be better off parsing it on your own. Yes, sir?
We do a lot of reading in files that have text values, and then we have to generate some sort of ordinal number, for the text thing. Are there any convenience functions to do that for us?
There are. This load text method has converters that you can actually specify. And so whenever you see a value, you can provide like a function that it will actually take whatever the value is and map it to something else, do some calculation on it, and return actually what you want to do. So you'll use this a whole lot on dates, for example. You'll have something that's a string as a date in a file format. You'll provide a converter function that takes that date and actually, or a string of a date, and actually creates a Python date object. That's a typical use. For your ordinal example, you could write a little table that had, male maps to 0, female maps to 1.
We generally have to build that table. We don't know what the strings are going to be, so we have to build it. So,
You build it on the fly?
Yeah.
Yeah, so I mean, you might end up with having to do a 2-pass read, where you go and you read the data in, you get that column, and then there's a function called unique that will give you what are the unique values that I see, and then you can use that then to go, okay, these are 0 through 10 or whatever, and then use that to build that mapping function. I don't have a better solution than that. Has anybody else run into that and done a different approach?
Yeah, we just generally build a dictionary
Yes.
with an index value. But
Yep. Yes, sir.
When you compared the pill, and there was a sci-fi package that did the reading of JPEGs and PNGs.
Yep.
Is there a speed difference or with either of those particular packages? Or?
So the difference, in fact, the SciPy one uses pill under the covers. But pill doesn't pill has its own data format for images. So it creates its own thing. SciPy hands you back a NumPy array.
That's the key thing.
Yep, that's the piece there. So that's why we use this.
Total confusion when you use the pill and the
Yep. So this is the helper functions, the pill util functions inside of SciPy provide you. They give you, if you read a JPEG in, you're going to end up with a 3-dimensional array. You're going to have X and Y, and then you're going to have the red, green, and blue channel. And so you have 3 dimensions for that. Unless you ask for flatten, and you can say flatten equal true, and if you ask flatten equal true, then that will do x squared or r squared plus g squared plus b squared square root and get a luminosity value for you. Okay?
Thank you.
Yes, sir.
Does pill work with vector data too? Or
Does pill work with vector data? Give me an example.
like an SVG file?
Oh, no. No, it's a raster image reader on things. So if you had SVG, I don't know if there's an SVG reader. I bet there is in Matplotlib. Anybody, there's not, so Ryan might know. I don't know if there is. That's a bit of a tricky topic, actually. Any other questions? Yes, sir.
Just a little off the subject, but can you pass NumPy arrays to, say, C directly, or?
Yes. So that's actually the beauty of this stuff is, at the bottom. In fact, we'll talk about the memory layout probably. But at the bottom, you just have a pointer, a float star pointer or an end star pointer that has a bit of decoration description on top. But in the end, there is this raw pointer to your data. And so there's always some work when you call into C to deal with the transition from Python to C, but it's not like you're copying all of your data over or anything like that. And that's in fact how we get all of our speed, is that we're sitting on top of a raw pointer and we can ask compile functions to operate on those pointers. So this is why, in fact, this is why you're here. It's not explicitly why you're here, but this conference would not exist if NumPy arrays were not wrappers around something that could be handed to C. If that wasn't true, then there would be no reason for SciPy to have been created. In fact, if you look at SciPy, the library itself, there's a lot of Fortran code and a lot of C code that implement all of Bessel functions and Hankel functions and anything like that. And we just have this thin shim on top of that to allow those to be exposed to the Python layer. Cool? Anything else? You good? Okay, so array slicing, 2 dimensions. we have examples here. We have a 2D array. And in this array, what if I want to grab this orange box here? This 3 and 4. Well, I'm asking for the 0th row. We have row 0, 1, 2, 3, 4, 5. This is the 0th row. That's what the 0 is for. And then I want to slice out the elements 3 up to but not including 5. So index 0, 1, 2, 3, start at 3, 4, 5, up to but not including the 5th element. So that slices that out. Okay? The next one is 4 colon. So this is saying I want to go from row 4 to the end. Index 0, 1, 2, 3, 4 to the end. And the same thing on columns. So 0, 1, 2, 3, 4 to the end. That slices out this blue piece. Cool? How about asking for just the index 2 column? I just want this one. Well, I need to get every row, so I go from the beginning to end on the rows. And I want index 2 column. So that's this guy. And this one's kind of goofy. I'm asking for a checkerboard pattern starting at index 0, 1, 2, going to the end, getting every other value, and then starting at the beginning, going to the end in columns, getting every other value. Does that make sense for everybody? All right. We're not going to do this example either. There's another one, I think it's called filter image, that I would encourage you to do, but I'm going to draw it up here and we're going to talk about it in the same way that we talked about these 1D images, because this is kind of the intro, and if you get what I'm talking about here, then you are on your way. You got it down. So let's talk about an image here. And I want to do an image processing step on this image. And what I want to do is basically for each image, if I have a pixel, I want to average it with every pixel in its neighborhood. So we're going to average 5 pixels together. Now you can do this with a convolution kernel. That's one way of doing this. We're going to do this explicitly with the way that we arrange our arrays. All right, we're going to do it with slicing, basically. So the first question, to get details out of the way, how would I do this cell? Are there any issues here? If I wanted to do this one? You can't, can you? Yeah, you're kind of screwed. You don't have anybody to the left or above. So you could treat this with periodic boundary conditions, things like that if you wanted to be really fancy. We're not fancy here. We're simple. So what we're going to do is, when we can't do it, we just give up, right? So we're just going to do the pixels that have all of their neighbors. All right, so our image, when we finish with this, is going to be one smaller, or in each direction. So it's going to be 2 smaller in rows and 2 smaller in columns. Well, I'm going to just, for giggles here, we'll call this center. How do I slice out that center image? Let's call this thing image, the entire thing. One colon minus 1, I think I heard. Everybody agree with that? Will that work? So that's the rows. So that said, I want to go from here, index 1, to index minus 1. So that's these guys. That looks pretty good. How about in columns? You guys are on fire. All right, so we got it. All right, that's the center image. All right, I'm going to simplify the problem. We said we wanted to average with all of the guys. Let's just assume that we want to average with the pixels, and I'm going to draw this so we have a... Let's just assume we want to average with the pixels above us. Okay? So let's have, if I want to do this pixel, the pixel above it is this one, right? If I have this pixel, the pixel above it is this one. If I have this pixel, the pixel above it is that one. And this one, the pixel above it is that one. So it turns out that that is really the pixels above for each of these. So if you took these guys and thought about it, you can kind of think about laying these things down on their sides. And then you can add, you know, this one through to that one, 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 and then you're going to get a result that is your final image. If you added these things together, you'd end up with a new image that was the addition of these. So you're basically taking these things, aligning them, and doing the addition is one way of thinking about this. All right? So how would I get this upper image? What's the slicing? 0 to -2, or what's another way I could write that?
Colon -2.
Colon -2. And then how about columns? 1 to -1. So my center image and my upper image, and I could write my new image here, if we were just going to average those two. And we just average those two images together. All right? So why don't we take, we're going to do this one quickly. I would like you to do this. It's called filter image. And you have that image to get. You have this image to grab. And then you have this image to grab. All right? Let's work for 10 minutes on this with your neighbor, and then we'll move on. We won't spend much time on this. All right, let's look at this solution right quick. If you're still working on it, please keep going, but I'll just go over this so we'll save a bit of time. So we talked about grabbing the center image. And so here we created an image, and then I've just created a function and passed that value in. So this is our raw image. And we're getting rows and columns, or slicing off the beginning to the end of the rows, into the beginning of the columns, just getting rid of the first and the last. And then the top image, as we talked about, we've already chose how we were going to get that. Now, the bottom one is very similar to the top, but we've got to go from here basically down. So we're going to start at index 2 and go to the end. And again, it's centered in the same way. Left and right are very similar to top and bottom. We just need to swap the row and column on things. So we add all those things together, divide by 5. And if you run through this, the image will be a little bit smooth, but you have to look really closely to see the smoothing that's occurring on things. But if you run through 50 times or something, then you will get a more and more, it's a diffusion. Of the image, and so it's smoothing out. And if you have a 255 or 256 by 256 image, if you run it, 128 times, then you basically have the world's slowest averaging technique. It's going to average everything out. The only got you is those edge elements. We're not setting those up so they're always going to have some impact on the image. But yes.
If you do it this way versus the convolution algorithms that are in what's sci-fi, is there a speed advantage or disadvantage of going one way versus the other?
I would expect the convolution filters are going to be faster. Yeah.
What is innately making those faster than this? This looks like it's fairly primitive and very low-level language programming. Why is it so much faster? Why would it be faster?
There's going to be caching that's going to come into effect.
you write it in C, you can write it to cache the
Very good.
Well, and the other piece is, I guess it's also going to depend upon the size of your template and that sort of thing. If you can do the FFTs on the convolutions and then bring them in the Fourier domain, do the operations there, you have a lot less operations to do. You have the FFT that you have to do. But, so, you know, unfortunately, with all of these questions, the active answer is it depends. It has to be the first thing you say on that.
Are the NumPy array operations multi-threaded?
No. There's a nice place that could be put in, but by default, they're not multi-threaded. You could set things up kind of to do multi-threaded on pieces, but by default, they're not. The convolutions probably, so EPD, the Intel Python distribution, links against MKL, which is the math kernel library from Intel. And there are some algorithms in it, like addition, subtraction, all of these things, they're not going to be multi-threaded at all. But things like a dot, or like an eigensolver, or a matrix multiply, those operations, nothing about NumPy is parallel, but the MKL is parallel. So we hand off our pointers to them and we say, go to town. And they do their magic on them. And so some of those are going to be parallel. I think the FFTs in ours is parallel because the MKL has parallel FFTs involved as well. That's one of the areas where there will be advancement, I am sure, over the next year or two to get that in place. It's kind of important now that people are not jacking up to gigahertz, and instead they're jacking up the number of cores on every machine. So, all right. So slices are references, and this is a big win and a place where you can shoot yourself in the foot. So be aware of this. Anytime you allow references in any programming language, you have the potential of saving memory, and you also have the opportunity for spooky action at a distance, right? You have two things pointed at the same set of data, and you hand one off to some other algorithm. It starts doing things. It can change something, and then you go look at the other variable, and you're like, hey, I didn't even touch it. Why are these values different? And the reality is that this other reference to that data somehow changed it. So you need to be aware of this. But there's also a big win. And that is, in scientific computing, just one second, in scientific computing, you end up with a situation a lot of times where you have one data set and you need to have multiple references to it because it's a gigabyte in size and you can't afford to have copies of it running around. So by default, or the slicing notation in Python is going to be references to the original. Yes, sir?
Yes, if you have a nice long convoluted bunch of control flow and you get to a certain point and you actually don't know if what you've got is a slice or a copy of something, is there a way of actually querying it? Let's say you've actually accomplished all of this and you're in PyLab, you just right there at the Python command prompt, can you actually query, are you a slice or are you a copy?
There is, I haven't poked around on these in a while, but yes, there is, like if I have A is equal to array, and then B is equal to A, so A dot base is none. So it will point back. It doesn't give you the name was A. All it knows is what the object was. So it tells you what the base object. And if you allocated the memory, then your base is going to be none. I would also say I can't think in 10 years where I've written code that I've done this as a check. So that's just a little alarm goes off in my head to say you probably don't need to do this unless you're doing something where you're passing things into C. Like you should never need to do this at the Python level. You probably ought to read or at least consider what you're doing to make sure, do I really need to do this, or is there an alternative path? So that I don't have to make code that's explicit to one of these or the other.
Usually your function either is supposed to destroy the array or it's supposed to leave it intact. And you know when you write the function what you want to do.
If it's in or in out or whatever.
Yeah. And so
well,
you
and
have a copy function. You have a,
that's right.
there's
and
a
you
copy
just,
function or a deep copy. That
there's
you
a
use
copy
if you want
function.
to have a,
yep.
if you want a,
If you
want
need
really
to make
replicate-
sure that you have your own version, then you can copy it.
What is
and-
that function? Copy or?
It is indeed. So if you do b.copy, then, or if I say c is equal to b.copy, now it doesn't have a base. So that's forcing, I want to make sure that I have my own copy of this data and that I'm not a reference to anything else. So that's one way of doing it. The other one is you can do array, and on the constructor, there's a way to pass in copy. And so if you have another array that you're wanting, if you just say array and another array, you're going to get a reference to it. Like if you say array A, oh, I guess you don't. Maybe you have to do copy equal false. Oh, I needed to do. I'm surprised by both of those actually.
Well, I think the problem was back there on 139, you thought you were saying C is equal to A dot copy.
Well, but I have
B was just a
A.
reference, B was just a view.
Well, but if I say print d.base, it's going to give me none. So I would have thought the copy would have. That's definitely going to give me a new one, which, but the other one I would have thought would have made a reference. I'll have to look at that, why that doesn't happen. But you can always use copy to force yourself into a new domain, or copy of your data. Okay? All right. So there's slices. So be aware that when you have a slice, you have A, you slice out B, you make a change to B, you have, ooh, spooky action at a distance on A, all right? You modify B, A gets modified as well. All right, fancy indexing. This is another really cool thing. It also, I'll have to say, ignore all that stuff I was saying about copies and references after I show you fancy indexing. So there's a bit of a wart here, but the power of it's awesome. So imagine I have an array here, A, that has 0, 10, 20 up to here, and I just want to grab this element, that element, and this one. Well, I want the index 1, 2, and index -1, 2, 3 elements out of there. That's what I've gotten here. I can actually specify this as a list or as an array of values, of integers. And then I can index A with this. So instead of doing a slice or a single value, I'm actually passing in a list of indices. And that gives me back those values. All right? Pretty cool. It turns out that this one is a little cooler. And that is, if I have a mask that happens to be the same size, we haven't talked about this, but I created an array here with these values, 0s and 1s, and I've specified its D type when I created it. Instead of integers, these are Booleans. So these are flags, on, off, true, false. So if I use this, basically, I've selected out the same values that I selected with 1, 2, and -3. So this works just as well as this works. Okay? Yes?
There's some way that I can pass a lambda expression to that so that I can have my own calculated mask without actually having to create basically an array that's the size of my original data.
Is there a way to do a lambda in that? No, there isn't currently. There is, so one of the things that has been passed around, and I have no idea, as a really nice feature at some point would be to have calculated columns and structured arrays. We're not two structured arrays, but instead of actually explicitly making it, say this is actually, if you had X and Y and you wanted another value, then you could actually make that an expression instead of x and y, and have that calculated on the fly. And now that's vaporware. It doesn't exist, and it's actually hard to do. But there's interest in that happening, and so that may happen at some point in the near future.
So if we needed to do that now, the way to do it would be do one pass to create a mask.
Yeah, let me just do an example here where, okay, so we have x is equal to lin space, clear. And then y is equal to sine of x. And so I can say plot x versus y. I get my beautiful sine wave here. Very impressive. And then somebody comes along, and this is where things start getting interesting. Somebody says, well, where are these values? Where are the values of y greater than 0? And so you can say, well, y greater than 0, greater than or equal to 0. And you get this mass that's true, true, true. And I can assign this if I want to. Y is greater than or equal to 0. And now I can come along, well, let's see where those are. And I'll say, well, plot x where that mask was true, and y where that mask was true. And do that with red circles. And there they are. So you all of a sudden have actually a very nice querying mechanism. It's almost like you have a little, instead of having to put things in an SQL database and then do SQL queries on them, you have this quick way to do querying of your data in this way. And you can do things like this, where you say, my mask, I want to see where is y less than or equal to 0, and we do x greater than or equal to 3 times, or 2 times pi, 3 times pi over 2. Oh, is that I have to do, what is that? Oh, no, I have parentheses, thank you. My brain is halfway in C and halfway in Python. So it turns out that this AND operation binds tighter. We actually are doing the AND with the 0 and x, and you always have to pay attention to this. Whenever you put an AND operation, this has higher precedence than the greater than or equal to. So whenever you're doing these Boolean combinations, you always want to put parentheses around your sub-expressions here. But now that's my mask, and if I go back and plot these, and we'll do a green, it's just these guys. So we've kind of combined 2 masks together. Yes, sir?
Just checking that I understand it right. The mask is static, right? If the underlying x and y gets changed, it's not going to regenerate.
That's right. This is a computation that we're doing. Yep. Everybody cool? All right. What's next? There is a great example. Oh, let's look at this, and then we'll talk about the great example. We'll probably not do it. So it turns out that there are 2 things to know about. One is, how does this work in multi-dimensions? All right? And this is how it works. Anything, so here we have A, which is our array over here. Imagine I want to get this diagonal. So we're off the main diagonal by 1. Right? What I can do is I can specify a series of rows and then a series of columns. And if you zip these 2 together, 0, 1, 1, 2, 2, 3, 3, 4, and 4, 5, that would be the indices of each of these elements. So you specify the rows and columns separately. You have a row entry, column entry. You zip those together, and in fact, that will give you this diagonal. There's actually a method called diag that will give you the diagonal of an array, and you can add, and that will give you the main diagonal, but you can ask for -1, offset equal 1, or -1 that will give you above or below. That method works just as well as this for querying. The difference is that will give you the values there, but it won't allow you to write to them. In this case, like imagine you're doing some implicit time stepping scheme on a finite difference equation. You set up your linear algebra matrix and you know what all the diagonals are supposed to be. This gives you a nice way of going in, selecting the main diagonal and setting the coefficient along that diagonal, and then walking, either side to set up your coefficients and you can write into them, because you could have this, if I said equal 4, that would make all of these values 4 here. So that's a nice feature to know about. It's not quite as convenient as you'd like it to be, because every time you go off a diagonal, you have to kind of do some calculation to find out what the indices are that are there. But it is a nice capability. You can also mix, so we have this fancy indexing scheme here. We're mixing fancy indexing with normal slicing. So 3 colon here is saying go from the end of the array, or from 3 to the end of the array. And in this case, we're choosing to get the 0, 2, and 5th column. So that's selected out this blue set of data. Cool? The same can happen. Here we've made a mask, and I'm going to use this mask to say, you know what, I want the column 2, but give me the 0, the index 2, and the last value out of this. So here we're mixing just a scalar with the mask. Yes, sir?
Sorry, I have a stupid question. So what's the syntax difference between the first and the second that gave you back a 1D array versus a 2D array?
From here to here?
Yeah, it looks like the second one you got back a 2D array.
I did. So in this one, I am specifying these are, you can think about this. Let me just do this real quick. Where is this shape from that? So you can actually set the shape on an array. This made an array of just 1 dimension. I'm going to make this. Oh, what did I do wrong here? Do I not have? Oh, I didn't do that right. Okay. I was like, this doesn't work quite right, does it? So 6 by 6, that's going to be. Eventually I'll get there. All right, so that's a 1D array, but I can come in and do the shape. And I can say I want to have 6 columns, and the way I do that, if I specify -1 for the rows, I'm telling it, I don't know what it is, you figure it out. And then give it 6. And now if I go and look at the shape, it's 6 by 6. And if we go look at it, it's that shape. Okay, so now if I come in and I want to grab, if I come in and say, let's say I want to get the first 4 elements out of this. Like the first 2 rows and the first 2 columns. So I just say :2, that slices out the first top quadrant of that, right? Let's say I wanted to get this element and this element out of here. Well, that's a 1D, I'm asking for those elements out of the array. The way that I would do that is say I want a 0, 0 and 1 row, because the index of this one or the row index is 0, the row index of 7 is 1. Make sense? And then the column indices happen to be the same things. That's going to return to me, because I'm specifying each element, it's going to return to me a 1D array. Now if I came along and did this, so here I'm saying I want to get 0, the 0 element, the 1 element, and the 7 element. So I'm kind of cutting out this weird path. And if I do that, it's cutting out those elements, but it's always going to return those to me as a 1D array, because I'm specifying each element out of the array that I want. Does that make sense?
Yeah.
Now, if I go back over here to my pretty picture, in this case, I'm specifying I want these columns, but I specified in rows I want from here to the end. And so there, I'm getting all the rows and then these columns. So that's going to return to me a 2D thing. Does that helpful?
Yeah, thank you.
Okay. All right. It turns out you can use these, you know, we've already seen if I do :3, or I talked about it, I could index a row with just 1 if it was a 2D, and that would give me the index 1 row out of that 2D array. Slices work the same way. :3 will only give me the first 3 of these. I can also use a conditional array, or it will give me all the first 3 rows. I can also use a conditional statement to get the first index 1, 2, and -1 elements, or rows out of this array. So this is basically the same as saying a condition, comma, colon, which would say give me all the columns. But if you omit the columns, then it's going to give you all of the columns. Does that make sense? Okay. This turns out to be very handy, especially when you might do an operation and you want to find, you know, in your third column here, you have some data like rainfall or whatever, and you want to see where the rainfall was greater than 10. Give me all the years that rainfall was greater than 10. Well, you're going to go to that column, slice it out, and say rainfall greater than 10. That's going to give you a Boolean mask back. Now, once you have that mask, you have a mask that indicates which rows in your data the rainfall was greater than 10. You might want to extract those rows and get a whole data set. Of this data, I know all of the dates now, all of the information where the rainfall was greater than 10. So once you have that mask, you can use it to index in like this. That will grab all the rows, and you have the data set you're looking for. Cool? All right. Now there's a gotcha here, and it's down here in this bullet. And all the stuff I said about slicing being views, that's true if you do the colon kind of slicing. But as soon as you use a fancy index, which is a goofy name we just gave these things, where we're specifying multiple indices, you end up with a copy. You do not get a reference. The reason behind this is the underlying data structure for NumPy, which we'll come to, doesn't have a way to represent non-uniform striding along a dimension. And so it just can't do this. The only way to support this is to make a copy when it gives the data back. In the end, it was chosen to go ahead and do this because the power of this is so high, we can deal with this warp. Over time, again, this is one of the things that could change over the next X years, where we get something in place that the underlying NumPy data structure could actually handle this. Yes, sir?
So what you're saying is this is basically like a gamma, bring together all the data that matches.
That's a good explanation of it. Yep. It just is going to grab those things and create a new array. Yep. All right. Yes, sir.
I was going to add it. You can use the optical mask tool.
Oh, like the tilde, you mean?
Yes.
Yeah.
You can still use the other side of the data.
That's right. You can, if you want to invert the mask, the inversion operation for Python is a tilde. And so that will give you where there were zeros, there are ones, where there were ones, there are zeros. You can use that to index in, and that gives you the opposite set. And that's a very helpful thing to be able to do. Yeah.
How do you transpose the map?
There are a couple of ways, but the most common way is a.t. If your array is a.t is a transpose of it. So if I have my array here, if I do a.t, that returns to me, it's a capital T. This is a transpose of it. There's also a.transpose. Either one of these. And this is actually a reference to the original data. So it's not a copy. If you want to get a copy, then you have to do a.t.copy. And now that's going to be a copy of the data.
Is there any way to eigenvalue?
There's a function in SciPy. I think it's also in NumPy. There's an eigen, or eig, E-I-G, is the name of the function. Yeah, sure is. There was another question. Yes, sir.
With the mask operation, is there anything created under the hood to track the provenance of what you did? Since we're just getting a copy.
that would show
Like
you?
what the condition was?
Not at all, no, because the condition you're defining, like when NumPy gets things, it just gets the mask. It has no idea where that, what the expression that created that or
So that
anything.
would be metadata with the mask. If it was-
There would be, yeah, I would argue that if you're trying to do that, the best way to do that sort of thing is have something that generates the script. Because you can read down the script and you can see exactly what happened. A greater than 3 or whatever it was. That's one of the cool things about dynamic languages. There's the provenance issue that everybody deals with. Python, because it's a dynamic language, provenance is really hard. And I think, honestly, the best way to do this is to be able to generate the script that does the queries and data calculations you need, and then store that out with whatever data you have. All right? Yes, sir?
How to write complex numbers?
A complex number. We have a session on or a section on that, but we probably won't get there, so we'll talk about this. If you want a complex number, you put J. So I apologize if you're a mathematician, the physicist one. So you have to do J. You can't just do J by itself. Why not? It's the variable J. And so you have to prefix it with 1J, and so you do 1 plus 1J, that sort of thing. Okay? All right. The great example that I was going to, is useful. There's one called Dow selection that you go through and find which days the Dow is greater than a certain volume or whatever and create a plot. And regardless of whether you like that world, it's a very nice example of the kind of querying that you can do. It will exercise that part of things really well. All right, where is useful to know. Where it's going to go through a greater than 10, you get this Boolean mask, but you might be wondering, where was it true? What indices? 1 and 3 in this case. Well, the where function will tell you a greater than 10. Where basically is something that goes through and tests for non-zero. So in fact, if you have something with zeros, 1s, and 2s, and 3s, it'll give you true for anything that's non-zero. So we get back an array of the indices. There is a gotcha here. And that is, it doesn't just give you back the raw indices. It's kind of like shape. It gives you back a tuple. And this is very painful when you're dealing with 1D data all the time, because you will end up writing a whole lot of this, where a greater than 0, 0. And this is this gives you a tuple with the indices as the first element. This gives you that back, and that gives you the indices. So it's goofy, but it actually, or it's painful when you're dealing with one dimension, but in n-dimensional things, it's exactly what you want to get back. And so in that case, this gives you back a set of the rows and indices where this statement was true. Okay? All right. We have 20 minutes. And there are money manger things. Let's talk about this. I think there are enough people that deal with the low level to I'll try to keep it at 10 minutes and then we'll go over the other main thing that I want to get through today. So we're going to dive deep. We've kind of been talking about API level things. It's really useful to know what the heck's happening under the covers. How do these NumPy arrays work? Especially when you have people asking questions about, can you deal with C? How do you hand this off to C? Well, if we think about memory, memory is just this one-dimensional thing. You have an index space that starts at 0 and goes up to some big value nowadays, 16 gigabytes or whatever it might be. And if you think about that, you have these values laid out in here. That's a horrible one here. One of these black ones is really good. That one. So you think about memory going off into Never Never Land here. And somewhere in this memory, you start writing bits, and we forget how many levels of abstraction we're actually working with when we get to C. But somewhere somebody decided that charge existing versus charge not existing was ones and zeros. Those ones and zeros we arbitrarily gather into 8 elements and use those as a byte. We arbitrarily then take those, it's not totally arbitrary, but you can make completely different choices. I read an article recently that it looks like the brain's bytes are 6-bit, which is a really interesting notion. So why did we pick 8? Don't know. It was a multiple of 2, right? Seemed about the right size. So we get the 8 bytes. Now we take those, and 8 bytes is typically not quite enough to represent some number we want. So we gang those together into 4 of those, and we call that an int32. And then we choose the encoding. Is it 1's complement? Is it 2's complement? I mean, holy cow. We're like way up this abstraction layer, and in fact, everybody in CS thinks this is the bottom of the abstraction layer these days, right? So you kind of forget how high things go up on these layers. But we end up with these 8-bit things, and every byte, you know, we have each one of these is byte 0, 1, 2, 3, or whatever, and then we have some break. And in this, we're going to have these things being 0, 1, 2. We're going to treat these groups as an int32 or a float32 or whatever it is. And then we have a sequence of these things. And if we have something like this array here that has this shape, we have to describe in Python, you have to have a header that says, take these bytes, which are the fundamental piece of your computer, and describe how I get to the fact that they're a 2-dimensional array of int32s. That's the information we fundamentally have to have in place. Okay? So if we think about that, this is how we do it. This isn't quite the full data structure, but what happens is NumPy has this data structure that is used to represent or to inform you about how this, you know, this is your low-level pointer here, your void star, basically. But it's pointing to bytes that can be represented as 0, 1, 2, 3, up to 9, 8 in this case. How does it know about this? Well, the first thing is there's this thing called a D-type. And the D-type points at yet another data structure that is a data type. In this case, I call it float32. It could be int32 or whatever. But the first thing this does is this informs it how big every element in this array is going to be 4 bytes, and I want you to interpret that as an IEEE 754 floating point number. Okay? The dim count, I know that this is a 1D array, but I want you to treat it as if it's a 2D array. And then I come along and I tell it, well, it has 3 elements. It's going to have 3 items in each row, and it's going to have 3 columns. So we've gotten that in. And here's where the magic happens. Initially, this looks superfluous. And we are so happy that Jim Huguenin put this in. This is the idea of strides. And strides tell you how far you have to go. If I take this data, three, 4, 5, 6, 7, 8. So I have all of this memory down here. The strides tell me that first stride tells me how far do I have to move to get from the first row to the second row. And so if we look in here in memory, that distance is 12 bytes. We have 3 elements, and they're each 4 bytes long. Okay? And then the second piece of information in the strides, we had that as 12. And then the second is 4, and that tells us how far do we have to go from this element over to that element. And in fact, you know, these guys are neighboring. You just have to go over 4 bytes, and you're to the next guy. Now, that seems somewhat superfluous because we just told it it's a float32. We just told it its shape. Isn't that enough? Well, the gotcha here, and the reason that this is the way it is let's look at, if I call this array A, let's say I have the array B is equal to A, and I'm going to do this where I say I want all rows, but I only want every other column. What values is this going to be? What shape is it going to be? Let's fill this in actually for the data structure. What's its D type going to be? D type. Float 32, that's great. What's its shape going to be in dims? Say, I think I got it.
3 by 1.
Not by 1, right? It's going to have, this line is going to give me every row. And then we're going to start at the beginning, go to the end, and get every other item. So that's going to give me this one, and then this one. So it gives me the even column indices. Does that make sense? So what's its shape? Or what's its, it's two-dimensional, right? I may have missed on that. And shape, somebody probably told me the right thing. I was not thinking about it right. I was there. What's its shape going to be? What are the elements going to be in it? 0, 2, 3, 5, 6, 8. Right? So that's going to be 3 rows and 2 columns. 3 rows and 2 columns. Because this thing, if we just look at what this is, it's going to be 0, 2, 3, 5, 6, 8. Does that follow for everybody? Okay. All right, so we've gotten shape, we've gotten, data. Let me do this one. You know, the data for A is just pointing at the beginning of this array. Where is this going to be pointing?
Same place.
Same place. Wonderful. All right. Wake up, put your thinking cap on, and tell me now, what are the strides? 12 and 8. So the idea here is we're pointing at the same location. If I want to go from 0 to 3, I have to move over 12 bytes, even though there are only 2 elements along that column, or 2 columns. Because I have to skip over this. Only this one and this one are important for me. But still, in the memory layout, I skip all the way over to here. So this is a non-contiguous array now. There's actually kind of pieces of it. It's ordered, but you can't just scan through the memory and take every element out of this. And then the second, the 8, is 0, 1. This is 4 bytes over, but we skipped this one. We don't want that one. We actually go all the way over here. And that's going to be the stride. Okay? Yes, sir?
Are bools bits or bytes?
They're going to be bytes. Yeah, it's just too much work. You could save 8 times the memory, but the hardware cost would be too, or the computation cost would be very high. There is a library called BitArray that you can use that does pack things. But it's, typically you won't see that used. Yes, sir.
So you were just talking about packing. Make this more compressed. Get rid of those JSON areas that you're not using.
Yep.
Is that what you're talking about here?
No. He was saying like if you had a Boolean array where you just have 0s and 1s, you know, you could store within a single byte. You could store 8 of those 0, 1 in there. But NumPy treats the smallest data structure is 8 bits long. And so if you have a Boolean array, it's going to use a whole byte to store the 0 or the 1.
Okay, so my question then is there a way of compacting that B array so that you can have a more effective, it's just a reference?
So if you do copy, then, so this is actually going to increase your memory footprint, not decrease it. Because A still exists. This A has not been deleted.
But if you delete A.
If you do, I mean, if you did something like this, where you created A up here, doing something, and then you do A dot, or del A, if you don't have this copy, B is still using that memory, so it's going to keep the entire footprint around. And if you don't want that to happen, then you can do .copy right here. That's going to just make a new set of memory completely independently of this one. You now have B pointing at this.
You have different strides.
You would have totally different strides. Yeah, you would have 8 and 4. And now you would delete A, you've gotten rid of your original, and now you just have that piece.
You
Cool.
did A equals A with the copy there, would that do the same thing there? Would that,
If you said A equals
A, some slice dot copy.
like this,
Just B is an A now.
I don't quite follow.
So just erase the B and have it be an A there? Or that A equals A,
Oh.
slice and a copy, what would that do?
It would create the array, and then nothing would be holding a reference to it. So if you're running a script, it would be created and then released. If you were doing it on the command line, it would now be associated with the underscore variable or the underscore out 12 or whatever. IPython actually, this is one of the places you can get in trouble with IPython. If you're using large arrays, it's actually keeping a reference to those to help you, because you might want to go back and get that sometime. I want to see what I did 30 times ago. When you do that, you know, you can kill memory really quickly because you're not getting rid of things. You think you deleted A, but actually A is being held on to by one of these guys. So be aware of that. All right, one more question on this. I had a question in the back about transpose. So what if I say B is equal to A dot transpose? It's going to be float 32. Its dimensions are going to be 2. And this gets back to your question about column versus row major order. What's its shape going to be? 3, 3. What are its strides going to be? 412. Does that make sense? What we've done there? We've just switched the strides. We're pointing at exactly the same location. If you want to go over in this, you know, let's just draw what this looks like. It's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. If you want to go to the next row, you move over 4 bytes. If you want to go to the next column, you move over 12 bytes. So the transpose is just a reference to the original array. And this, because they had the foresight to put this strides information in here, it fits both models. That's really cool, actually. This is a big deal. I mean, this is there. It's also, because we only have information about a stride, like this is the stride between every element in the row dimension. And so this is impossible then, this is why it's impossible to have kind of 1, 2, 4 or whatever when we're trying to, this is why the fancy indexing, there's no information to store multiple sets of offsets for each one of these things. That's why fancy indexing is a copy. Yes, sir?
So does that mean the transpose is relatively cheap?
It's wonderfully cheap. Yeah.
Even for huge, it's still.
It's just peak. That's all it is. All right. There's also something. Let me just do this. There's a library. All right, I'm not going to do it. I want to, but I'm not going to do it. So there's another library I'd urge you to go look at it called Stride Tricks. And Stride Tricks actually will do things like allow you to take a 1D array and have, instead of, you can take this array that's one-dimensional here, and imagine you're trying to do some windowed operation on it, where you basically want 0, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, and so on. But you don't want to make a copy of all of these things. You just want to have this one set of data. You can actually do this by saying the column offset is 4 and the row offset is 4. And so you have overlapping array or values that are, this value and this value are actually the same. If you change this one, you would change this one. But the array allows you to do this. And the really slick thing about this is what I need to talk about, and that's why I'm not going to do this too much. But there are operations that allow you to do very quickly. If this is my array A, if I want to know the sum or the average of these windows, I can do A.sum axis equal 1. This is the index 1 axis divided by, A.shape 1. And I've just done a moving average window on my one-dimensional data. So I've reorganized it in a way that NumPy operations work very nicely on it. So as you start realizing what the underlying structure is and how you can utilize this, you can end up with efficient operations and very concise in how you specify them.
So how do you print, if you have done some arbitrary slice, can you just print out that data, those values?
All of that data? Well, you can always do like A.strides. So that will give you that information.
Oh, okay, so you just access the member variables? Or
Basically, yeah. And you can set this, it used to not be settable. I think it's settable now. I always just go to, I think it's NumPy. So stride tricks is your dastardly opportunity to muck around with the internals of these things. Okay? All right, I do need to cover one more thing. Do you mind if I keep you 5 more minutes? Is that okay?
Go for it.
All right. There's a lot more to cover, but I really want to talk about so this is the other major kind of piece of things, and this are the numeric operations on arrays. So if I have an array, we'll just go, if I have an array called A, there is a function called sum that will sum up the values in A. And by default, sum sums up everything. Doesn't matter how many dimensions the array is, it's just going to take all the values and add them together. So we add these up and we have the value 21. We can also sum up A along the x, or the 0th axis. And the way we think about this is the 0th axis and this is the 1st axis. So when you say axis equals 0 for a 2-dimensional array, you're going to be summing along the rows, or you're going to be summing up columns. It's always hard to say exactly how you say this, but each column will get summed up. So 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. You can also sum up along the axis equal 1 dimension, or the way that I typically say it is axis equal -1. You remember Python allows this counting from the back. So almost always with your data, you're either going to be summing along the 0th axis or the last axis. If you write things and you pay attention, you can often write generic functions that don't care what the dimensionality of the data is coming in. They'll work for a 1D array, they'll work for a 2D array, they'll work for a 3D array if the data is arranged the right way. And so it's convenient to be able to say axis equal -1 to always get the last axis. You also can spend several hours of extra time trying to figure out how to make your stuff generic to work with anything, and you really don't get any win. So, that's what grad school's about, right? So it may not pan out quite the way you planned, but I typically still do this. And so we're summing along the last axis here, 1, 2, and 3. It's going to sum to 6, 4, 5, 6 to 15. There's an equivalent version that's a method. And these are completely synonymous with one another. The only benefit to this one is you don't have to import sum. Like sum is a function. You have to say from NumPy import sum at the top of your script. In this case, the array just carries it along with it. All right, and we have product as well. There are a whole bunch of these methods. There's sum, there's product. Those are the main ones, but you're going to have min and max as available functions. And then argmin is a nice one. Sometimes you want to find out what is the, instead of what was the value that was the minimum, what is the index of the value that was the minimum. All right, so that works for that. And then you have mean and standard deviation and variance. And there's an average that's around for historic reasons. There's no difference between mean and average, except the average allows you to assign weights to things. Okay? All right. So there is a great exercise that you should write, or you should work, and it's called win statistics. And the whole idea in win statistics is you're going to get this set of data that has months, year, and day, and it's what the wind speed was at 12 locations around Ireland between 1960 and 1978 or something like that, every day. And you go through this exercise, and it's going to ask you to do, give me what the wind speed, average wind speed in Ireland was. So to do that, you're going to take the mean of the entire data set. Now it's going to ask you, what is the mean in Dublin? And so you're going to have to figure out which column is Dublin and ask for that. Then it's going to ask you, what is the mean for each day? Like, what's the mean wind speed in Ireland for each day? And so now you need to do your averages along this direction. Then it will say, what is the average wind speed in January? So now you're going to have to mask out the data that's only January and then do your means on that. So if you walk through that exercise, then it will solidify what we're talking about here, and you'll have experience there. So you will have gotten from out of this, you know, I think the calc derivative, you've gotten plotting, have at least a basis for that. The calc derivative and the image filter examples are really nice for getting into your head, how do these slicing operations, how do I do slicing to replace looping, basically. That's the whole key there. You have the Dow selection example that you should work through to get comfortable with the fancy indexing so that you can select regions that are based on Boolean mask. And then you have this example to show how you do sums and means and that sort of thing across the different dimensions. So there's a whole lot more. We just need another half hour, we need another half day to basically get all those pieces. But there's structured arrays, there's broadcasting, I would encourage you to look over. And then there's memory mapping. That's a great way to read binary files. It's what we do for all of our binary files now. Always use a memory map on things. And those are the main topics I think that we didn't cover. A lot of the other pieces, oh wonderful. I'll upgrade to menu 3 right after this, I'm sure. The other thing is a lot of what we didn't go over are just APIs. These foundational concepts are the things that kind of twist your brain. You have to figure out. Once you figure those, then you can just set those APIs on top of this. And you can just read through and find the API you want. There was a question I saw. Yes, sir?
What's the equivalent of group by?
It's group by. So there are some APIs somewhere, and I can't remember where, that will give you a group by. You can basically think about group by. The masking that I was showing you is a group by operation, or that you can get a mask and then select those items out, and then that will group by whatever. I want to group by January month or whatever. You would have to have a loop that would go through and pick out January, February, make a mask for January, make one for February, make one for March. And then that would group those and select those pieces of data out. So you're going to have to write something for what I just said. There is, can you do it? Well, so that's the second place. There's also group by in NumPy someplace. I can't, Googled group by in NumPy. Somebody wrote, the reality is they're partial.
It's not a full kind of SQL implementation of things. The other thing is if you're doing a lot of that, pandas is it's the ticket.
Oh, okay.
It's the library that is for that. It works with time series. Wes McKinney, I think his talk, is it today or tomorrow morning? So he's going to do a lecture on time series, and he came out of AQR, which is a hedge fund. And so a lot of their data, they have to do a lot of things like we have data where things aren't lined up on the same dates, but I still need these data kind of organized this way. So it allows you to make tables with that and then query those tables, group those tables by different fields. It's very nice. Really, really powerful. That would be where I'd go. What else? Any other generic questions? Yes, sir.
Utterly generic. Can I find your slides somewhere?
I think they're in the pack that the zip file. There's a PDF of the zip file. Isn't that true?
Yes.
Okay. So the zip file that had all the exercises in it at the top level of the directory, should have been the PDF book. Yes, sir.
Very bizarre question. The thing about Python, you can do object-oriented programming. You can imagine objects which are data rich.
Yes.
You want to put all the data into something that's going to be really efficient.
Yes.
You still want to be able to reference the level of the object. That's kind of not going to work. So where's a good source to read right now?
Ooh. So, this is a wide and woolly topic, I guess. And it gets down to the architecture of what you're trying to do. Generally, what we find, I will tell you over time, is you want to have your data in NumPy arrays. It turns out to be very painful. Everybody always comes up with their own higher level version. My domain, I need to have an astronomy image because I have all of this gain and different things. Whenever you do that, do you want to take an FFT of that image? Well, dang it, I can't just pass in that thing. I have to go and grab the data out of it and pass that in and that sort of thing. It becomes a fairly large headache. One of the things that have been done on multiple occasions, people just will attach a dictionary to an array, and that dictionary will sort of flow through calculations under the covers, but it'll sometimes get lost too if you have two things that don't agree. It's a hard problem. I mean, what I have ended up doing, I've made the mistake of making high-level functions in geophysics, for example, for seismic surveys or for well logs. And I always end up wishing that I had just made a NumPy array and then had some dictionary sitting around that had that information about what the metadata for it was. So I'll say that try to fight your instinct to make these big high-level objects all over your code. And try to stick with NumPy arrays as much as possible. This is not, it's going to be different in every domain. But I've learned that over 10 years, every time I end up with these high-level data structures, I get frustrated at some point. Did you have a question?
No, I was going to say, it's easy enough to suppress the array.
It is easy enough, but there's a huge headache there. Because what do you get back when you pass in your array into an FFT? And then you get something back. Does the data that do you propagate that information along? Like now you have all of SciPy that you have to delegate over to a new thing. Or if you say A plus B and A is one of your things and B is one of somebody else's things, they add together, they have different kind of metadata. Who wins? How do you combine that? There's probably a generic choice that we can make. This is such a fundamental thing that we wish we could do. I think we ought to have a default, honestly. I think there ought to be something that carries this dictionary of data around. I still don't know how to do it. Every time I think about it, I end up with a bad solution. So maybe you can pull it off and we'll... but this is a fundamental problem that I wish was easier. What else? All right. Well, I've thoroughly enjoyed myself. Thank you so much for coming. sorry we didn't get through more data. If you have a specific question about something that we didn't get to, and it's something that I can answer quickly, then just come on down and we can go over it. And I'll also be here for the next 4 days. So look forward to seeing you at the conference.
Thanks.